Okay.
This meeting is being recorded.
Right. Yeah, so we are very privileged to have Russell Ali with us. Russell has a wealth of experience in production logging and interpretation. He has worked for Schlumberger as one of the companies that you all might be familiar with, and he currently is retired, but he consults with the local company Tucker and do their interpretation, log interpretation. Um, I have worked personally one-on-one with Russell when I used to work in industry, and I can tell you that his professionalism, his insights, his willingness to share has always stood out. And for the last few years, Russell has been providing his expertise, his knowledge, his experience for free as a guest lecturer in my class. And I hope he knows how much I appreciate it and how much the students appreciate um, what he does for us. So without any further ado, please welcome and pay a lot of attention to Mr. Ali. Over to you, Russell.
Okay. Thank you. I mean, I have difficulty sharing. You have to give me some kind of sharing option or something.
Yeah. Um, I probably do. Let me.
I think I post disabled participant screen sharing. That's the message I have on my end. Yeah.
So what I did is I made you a co-host, so you should be able to share there. Try that.
Okay.
I tried that this morning in another conference call and it worked.
How is that? Anybody see the screen?
Not yet.
You see. Any difference there?
Mm-mm.
Yikes. You are doing Stephen, hear me?
Yeah, I can hear you, Russell. What?
Stephen?
Yeah, we got a problem to share?
Yeah, not able to share the screen. They're not seeing there. I have the screen shared option.
Zoom is slightly different to Teams, but it should be similar enough that you should get it.
Okay, I got how's that? Anybody seeing that?
Yes, Russell.
Okay, good.
We're seeing your screen now.
Okay,
brilliant.
Great. Okay, great. Let's see the entire screen, okay?
Right. You could, depending on what you want to do, you could put it into presentation mode.
Yeah, okay. Yes, okay. Okay, how's that?
Right. Okay.
Brilliant. Good. Okay, afternoon, everyone. We just go through all slides. If you all at any time, if you have any questions at all, feel free to stop me anytime before we go further. So, Stephen's there with me. Stephen and I have been working for the last 3 years, so he has a fair amount of knowledge in production logging as well. Okay, so this will be the plan for today. So we go some basics of production logging. We will talk a bit about completion design, but not in detail, to show you where we run production logging, the kind of assemblies that we're working. Assemblies meaning what is the downhole jewelry, and show you some typical production problems. Then we go to describe the the tools, okay? And what I would say here now, my experience with wireline with whole case of logging, if the basic physics of the measurement remains with you, which is done for me for more than 40 years, you can understand logs for a long while and you give you an appreciation of if you understand how the instrument works, how the works, not electronics I'm talking about, the basic physics of the measurement, you're able to do any kind of log computation effectively. Showing what is done in data processing, in other words, when we take the data, what we do with the data before we give you something. And we show some examples in vertical wells and on horizontal wells, and some examples of what we actually have done in Trinidad. All examples that I will show would be what we have done in Trinidad. Okay, so to put in perspective what I'm sorry, what we do here, we have here what we call a flow of what goes on from the drilling stage to the completion stage. We have people know use seismic. When seismic, you have your maps and whatever. You go into your drilling, you drill a well, then you complete the well, and then you put the well on production. And the upper part there, you have open hole logging that is done when the well is drilled as open hole logs, resistivity, density, nutrient, stuff like that, to evaluate the well. Case two will go where you actually put the well, you complete the well. You run things like cement bond logs to see your cement isolation, and you put the well then on completion. When the well goes into production, that is here, that is when we actually will run a production log. The production log is run where the well is giving some kind of problem. Giving problems meaning the well is not performing as it should. For example, if you drill a well for oil that's making water, you have a problem. If you drill a well for gas that's making water, you have a problem. So production logs are what is normally run to that. So production log actually comes in the production stage of the well, when the well is actually put in production, it's making oil or gas, and production log is run, as I explained later, when the well is making some unwanted fluids. That's the actual application of a production log. Okay, for those of you who have never seen how logging is done on the left-hand side of the screen, I try to just explain basically what that is. So that, let's say the black line across horizontal line is the surface of the ground. This is your well drilled into the ground. Normally a well, when it's done, you have casing running there, like so. This is the K. You actually perforate the well. Perforate is a wireline terms. I'll explain what this perforate means. You make holes in the pipe using explosives that allows the fluid from down to flow the surface. So well as have some kind of control, this is your what we call your blood preventers and your assembly to control the well. Okay, so you want to run a production log or so what we have here now, we have an electronic unit here that stores a bunch of electronics in it that's very transparent to you. What we do here, the tools being what we talk about here, make measurements in the hole. So the tools are hooked up to this cable here in red. Tools are run down the hole with this winching assembly and then pull up or run down. And while it's pulled up or down, these pieces of things like a piece of pipe, they loaded electronics and all kinds of devices. They make measurements, and the measurements are sent on this cable. This cable has conductors, and this cable will then transmit this message back to this panel here, and it will then make what we call a log. A log is what you see the side here. So if I have to say, what is a log? A log is a measurement versus depth of some character, pull a spectrophysical character of the rock. So in other words, we will make a measurement in the rock here that tells you different qualities that's going on that the fluid has in here. And knowing these qualities, we can decide what is actually going on in the well. So to make it short, to understand what we're doing, when you say you're going to log a job or you're doing logging, it's done like this. The unit, the cable, the tool, it sends signals up hole here. If you really get very sophisticated, you have here we call you have an analog measurement, you have what we call digital analog circuitry that turns these things into ones and zeros. They come up the hole here, and inside of this unit, you'll have the reverse analog to digital to analog. Reverses that, it actually makes a log, which looks like what we have here on the side here, right? So that's actually what a log looks like. Okay. Okay. When you get into the industry, you hear people talk about real-time logging and memory logging. It's exactly what it says. In real-time logging, sensors downhole that I just showed, they have a transmitter that will transmit the data to the unit. So you see what something we call in real time. We have what we call memory logging. Memory logging, there's no conductor cable, and the downhole sensors send messages to this downhole memory. This downhole memory is then pulled, and it is read after the. You ask, what is the difference? What is a lot cheaper than the other one? One requires a lot of equipment. In other words, if you have a big rig, you might go and use a while. But if you have, let's say, a small platform or just a small structure, you do this on a memory board. Okay, so that is the difference between these two. You will hear those tools, that terminology used loosely in industry, are doing something in memory or doing something on wireline. Okay. Okay, what is production logging, right? It evaluates the digital production of the well, right? Why do that? You see exactly what the well is producing, right? You can do all kinds of things that I have there, doing oil, water, gas, whatever, right? But if you have to ask me in a few sentences, what is production logging do for you? Production logging does exactly this for you, right? If you remember this last sentence here, you've gained everything that we talk about. Production loggers will generally determine how much and what is coming from where. So we run all these sophisticated measurements, but all you're going to get at the end of the day is how much oil, how much water, how much gas is coming from each section there. Okay, so that's all. So if in a nutshell, you have to do that. That is your answer. Now, what we'll get, I'll explain this in more detail, but it's basically what you will see. On this here, these measurements here are depth, right? So 0 would be a surface, and this here would be further going down the hole. So what you will get here are some of these colors, and each one will tell you, for example, this is gas in red, oil in green, water in blue. Each one of these represent how much each part of this reservoir is contributing. For example, you would say at the bottom here, you're getting some gas, some water, no oil. That's up here. The oil starts to flow from here. You get more oil production from here. What you're seeing here in this well, you get all the water production from the bottom of the well. So it gives you an image of what is actually happening down in the well. For example, what is this telling me here? My well is making some gas, it's making some oil. So it's making too much water. So if you have to stop the production of water, all the water is coming from the bottom here. So effectively, the bridge plug is something set across here, well only makes gas and oil. So that's the way a production log generally is used to determine, as I said, what is coming from where, and it tells you exactly how much and exactly where it is coming from. Okay, let's look at some of the basic problems. Remember I said a production log is run when a well is giving unwanted fluids, is not behaving the way it's supposed to do, right? So I explain that. This is what you expect of a normal well. If this here was your open hole here on the outside black, the straight lines here, the casing run, normally this will be filled with cement in the annular space here. The well would then be perforated here. These horizontal lines are what we call the perforations. You'll have a tubing run down in the well, packer set here. So what you want, in the normal case, you want all these fluids, this oil here from these perforations here, to come up the hole and they produce well. Unfortunately, that is just pie in the sky. That's not what actually happens every day, right? So what you have is some of the problems. For example, let's look at this well here, okay? You see here, we have here perforations here, perforations there, tubing here. But if, for example, there's not enough cement in the annular space, you have what you call a channel in the annular space. And if there's a water stand below here, it allows the water stand from here now not having any kind of isolation. The water will now flow on the outside of the pipe and come through here and start to flow. So your well now, instead of making hydrocarbons, gas oil, now making water. After a long while, this well will be all for water. So if you run a production log in here, production log will tell you exactly where the water is coming from. Okay, let's look at that. We have what we call cross flows. So if you have these three sets of perforations here, and let's say this one has a different pressure, in other words, if one is depleted, and the flow will now, instead of the flow coming to surface, this flow will now go down, is what we call cross flow. So what you'll be getting, you're expecting your 1,000 barrels of oil on the surface here, and you realize I'm getting only 200 because this is now flowing downward. And there are no measurements that you can make on surface that will actually tell you what's happening here. On surface, you would know, okay, I am not getting the production that I'm supposed to get, but you will never know what is. For example, you will not know if this reservoir is flowing to this or this one is flowing there. Production log is the only thing that will actually tell you exactly what is happening. Okay, with the channel in. Okay, we show another example of the same thing here. You can have partial flow, some going up, some coming down, right? Okay, let's show the one. We have a lot of in Trinidad. You have here your casing here, and for some reason your casing may have a leak. For all kinds of reasons, you may have corrosion, you may have damaged pipe, and you get flow actually coming through here. Now, if there's a water stand here, the oil well or gas well turns itself into a water well. So what are you seeing there is production log will not only show you fluids coming from the well, where you know where the fluid is coming from, but also show you if you have mechanical problems in the well. In other words, if you have damaged pipe, if you have something that is causing that kind of thing, right? Okay, look at another one here. If the well has a plug at the bottom here, okay, and this plug is put for a reason to prevent water coming here. Plug is leaking here. You would now get fluids coming up the plug to the side here. If you have perforations like that, so the examples here, I can go with a lot of different examples, but it gives you an idea of what production logging is run. Okay, to put it back into your mind, it is run to find what is coming from where, but it also allows you to check the mechanical condition. In other words, to know if you got holes in the pipe, if you got bad perforations, or if some perforations are not there for some reason, right? Okay, let's make an analogy, right? When you run open hole logs, you run things like resistivity, you run the density, nature, and the gamma ray. So I think this list can go on and on in a positive fashion, right? And you take these measurements here and you make them into porosity rock, the volume, and the saturation. This allows you here now to be able to say exactly which zone has to be completed, in other words, which one you are actually going to flow. In production logging, we do exactly the same thing. We have a different set of tools. We measure the velocity of the fluid, we measure the capacitance, the density, the temperature, and the pressure. And we take all of these, and you can either go into old-fashioned interpretation, sequential type, solving equations. This is just linear regression, or you can go into some fancy program, and you can actually find out fluid ID. In other words, it's my fluid, oil, water, gas, and the actual rate. Rate meaning I can tell you how many barrels of water is coming from there, how many million cubic feet of gas is coming from each section. What most programs out there do, they convert the downhole rates to actual surface rates. So you can actually compare what you're getting at your stock tank against what you see downhole. Okay, that's it. That's my introduction to there. What I'll do now is go into the actual hardware. If you got any questions on the basics of it, right? So I'll revise the basics before you ask for questions. You got to write production logging. series of tools that you run in the well that answers exactly what is coming from where. It quantifies the amount of fluid coming out. It also identifies the fluid type, and it can also look for the mechanical conditions of your well. They're done in two modes. The two accepted modes in the industry are running what we call real time, what we call memory mode. Any questions? Good. This way. Okay. Okay, let's look at the basic. We're going to talk first of the basic measurements. Something called a spinner. Remember I said we measure the velocity of the fluid. So these are actual photographs of the pieces of iron, right? So you're looking at these pieces of iron. So these are the pieces of things that are actually run into the well. So this here looks like this here. You can see what it looks like in here. This here is an opening here. And inside of here is this piece of here, this piece. So the fluid comes into here. You go into the well, the fluid comes into here. There's a thing here, this thing here that turns, it comes back out of here. So what we are measuring there is the velocity of fluid by measuring how fast this turbine is turning. I don't know, I think around this time you see it around Savannah a lot. These people selling these little windmill-looking things, and you put it in the wind, it blows. It is exactly that. This here is a turbine-type blade, and the fluid is turning the turbine, and the turbine, we convert the turbine is making so many revs per second, right? Revs per second does nothing for it. We take our revs per second and we actually convert it into feet per minute, okay? So very, very simple measurement. We're looking at the way the fluid in the borehole is turning this turbine-like type blade, measure how many revs it's making per second, and we convert it to there, convert it into feet. Now, there's a way to calibrate this. I just talk basically how it's done when we go for it. So this here is actually what you will call an inline spinner. Inline meaning it is part of the tool. It is something that remains open all the time, and it's like one tool to the other tool. The other one, am I doing this? Yeah. The other one is called a full bore spinner. The full bore spinner is a piece of iron here. You got 3 or 4, depending on the tool, arms here. These arms open or close depending on the size of the casing. As these arms are closed, open or close, it closes this impeller here. Now, this is the blade I'm talking about here. And the fluid comes up through here, again through there, and it turns this thing here. And what we measure is the number of revs that thing makes per second. We convert that revs into feet per minute. So to remember what spinner does, the spinner has 2 types. You have what do you call an inline spinner, or what do you call a full bore spinner? Those are the 2 accepted names in the industry. The spinner is measuring the revs per second of a impeller type blade. We convert the revs per second in some program here that turns revs per second into feet per minute. Well, as we go down the interpretation, you can see we down the road change feet per minute into barrels or into cubic feet for day or whatever you want. Okay. I'm going to learn to get this right. Okay. We go to a little bit of electronics now. Remember, I said if you learn, or sorry, not learn, if you remember the basic physics of these things, you would understand it too. We have here a temperature measurement, and we have what we call a thermistor. Those of you, most of us study physics in school, and you remember that in electronics, you want to have resistors that are stable. They do not change the value with temperature. You want your electronic circuitry to be very stable. We have the opposite in this measurement. We have something called a thermistor. A thermistor is a resistor that would change its value depending on the temperature around it. So what we do is we take this thermistor, and this is a tool here, a piece of iron here, and this here is your thermistor. It's inside of an Inconel thing here, and the value of this resistor changes with the temperature of the well. So using that piece of physics, we're able to record the temperature of the well. And they are what we call very fast response time. They actually detect 1 degree change in a well. So they're very, very accurate. Now, what do we see in a well, right? Remember the Joule-Thomson effect, right? When you have throttling, you have gas expanding. So when gas is coming into into the formation or from the formation to the casing, you have a cooling effect. When you have water coming out, you see a heating effect. So generally, 99.9 times when you're producing gas, you see a cooling effect. So immediately see a cooling effect on a well, you don't have gas producing. Principle is very, very simple, as I said. It's a resistor that changes the properties with respect to temperature in the well. Okay, we all remember what in physics what they call the piezoelectric effect. And remember, we have crystals, right? You have, I think, it's quartz, and I think topaz are the kind of crystals they have. And in terms of electronics, the crystal is something that when you have mechanical forces impinging on the crystal will change its properties depending on the force applied to it. That's what the piezoelectric effect is. So we have in there, we call the quartz crystal gauge inside of this assembly here, and it's exposed to the borehole fluid. And as the borehole fluid changes in density, it changes in weight. For example, the weight of the column and gas will be different than the weight of the column and oil or water. So we actually use the principle here, the changes in the characteristic of a crystal to measure the column in there. We know that the pressure of the column we can measure. Now, if we know the deviation of the well, you can convert pressure gradient psi per foot to actually density. So the pressure measurements can not only give you the pressure of the well, but it can also give you the density of the column there. Okay. Okay, we go now to something a little heavy, right? Remember the reaction of gamma rays on atoms, right? We have three effects of gamma rays. We have one called photoelectric effect, the peer production, the Compton scattering. Compton scattering is used in open hole logging density measurements. What Compton scattering says is that if you have a gamma ray, there's a gamma ray source, let's say the cesium source we use, and you bombard anything else here, you interact with the electrons in the outer shell of the atom. Depending on the electron density of the element, you get either a decrease of the gamma ray that is reflected. So if we measure the gamma that is reflected after Compton scattering, it is the inverse function of the electron density. And we say electron density is equal to bulk density. Bulk density, we see it in open hole, and we see it in here. So what do we have here? We have a tool that looks like this here, this density tool here. And inside of there, we have a cesium source, very, very, very small. I think it's 150 millicurie inside of there. And we use the Compton scattering to measure the density of what is in the bore. Okay, so we have fluid coming inside of here, the detectors in there, and we have to measure what is inside of there. Okay, so we know what the density of oil is, 0.7 to 0.8, we know gas is this. So able to distinguish easily between gas and water or oil, right? So water oil looks almost the same to density tool. Gas looks very, very, very different. We measure something called the hold up, which we'll talk about in a while, okay? Okay, the other one brings you to what we call the capacitance measurement. And remember in electricity, we talk about the dielectric constant of element. Dielectric constant is a measurement of how well something can hold an electric charge, electric energy. Okay, that's all it is. But you have a capacitance that's electrolyzed at 150 microfarads. That's a measurement of how much it is going to hold that charge. So we have a series of plates inside of this thing here. We measure the dielectric constant of this thing here. And you see the dielectric constant of water is different to oil and of gas. Remember, I said just now, the density allows you to distinguish between gas and oil or water. When you have the capacitance now, the capacitance allows you to distinguish between water and oil. So if you have both of these tools, or you have measurements from both of these tools, you are now able to distinguish between gas, water, and oil clearly. So in a nutshell, we have so far, we have the spinner giving you the fluid velocity. We now have two measurements that combine together allow you to distinguish between oil, water, and gas, right? Okay, we have lots of people in industry, they do not want to run radioactive sources in the world. The world is getting very sensitive to things like that. So there's a new measurement called fluid density in nature. What that has inside of here, you remember what we call resonant frequency in physics, right? We have a tuning fork in there that resonates at a resonant frequency. It is found that if oil, water, gas passes over this tuning fork, the frequency changes, and the change is different for oil, water, and gas. So this allows you to distinguish between it. It has the same problem like the last one. Water and oil will look the same, very close to the same way, but gas would be different. The only advantage this has here is that in certain clients, certain contractors do not allow us do not want a radioactive source in there. So this here is the answer there. Sometimes you want to transfer something from one country to the next, you need a radioactive license and all kinds of things. And this allows that some airlines may not even allow it in the plane, okay? But it's not a very, very strong. Okay, these are the tools put together there. So what we're saying here, the combination of these two tools, of the density tool, either it's a radioactive tools or the inertia tools, together with the capacitance tools, they will allow you to distinguish between oil, water, and gas, which I just explained, because each one measures something else. The key to remember that the capacitance, this capacitance sometimes called the water hold-up tool, because the capacitance that is consist of water is about 80. Oil is 4 and gas is 1. So you see immediately it helps you to distinguish that. Here we go. So this is what I just explained, right? So you see clearly here, if you have capacity density here, that's oil, 0.7 to 0.8, what is there? So you see quickly, density allows you to distinguish between gas. Oh, clearly, these are too close. But you know, at the capacitance, capacitor now clears this up here. So you see clearly between that. So if you have these two measurements, you can distinguish between oil, water, and gas very easily by just knowing what is capacitance measuring, what is the density measuring. Okay, we have something called a CCL. CCL stands for the casing color log. Okay, casing color log is just an instrument. There's two magnets in there. There's a magnetic field in there. We will do from Maxwell's laws. Whenever magnetic flux changes, you get a current induced. So at a casing color is thicker than the rest of the casing. So at that point, you have a change in there. It is not used for any kind of interpretation. Casing colors and gamma rays are used only for depth correlations. You would see a lot of times on a production logging string, casing color, gamma rays, what am I running this? They are used for depth correlation. To just explain this point here, to use a wrong analogy, when you run an open hole log is like the birth certificate of a well, okay? In terms of depth measurement. So you have the depth measurements of the open hole log, all subsequent logs after that, the CBL logs, the caliper logs, whatever, and the production logs have to be on the same depth line. In other words, if on the open hole logs you have a sand from 8100 to 8200, on the production log, sand has to be at exactly the same place. So I use the analogy, you take a birth certificate and you're going to get your driver's license, you get your passport, etc., etc. So that's the analogy there, that it has to be there. So one thing we don't talk about here is something called depth measurements in the oil industry, right? And in the oil industry. So depth measurements is where you say something. It is good to say I have oil at 4,000 feet, but the 4,000 feet better be correct and not 4,050. Similarly, in production logging, any type of log, the depth measurement is very, very critical. It's what we call log quality control. Depth control is one of the things that you checked in the log. And when you start to work with logs, you realize that's some of the things that you always have to check. There's a gamma ray, and the gamma ray, it doesn't change over, I don't know, 50, 60 years. Gamma ray measures the natural radioactivity coming from the rocks, okay? Natural radioactivity comes from thorium, uranium, and potassium. In our environment, we are in we call a shady sand environment. So clays are the radioactive ones. The gamma ray has the ability to distinguish between sand and shales. So the gamma ray with the CCL casing collocator sees the jewelry. The gamma ray is the one that, as I told you, puts you on depth. Your log is now on depth with your open hole logs. So those are two basic stuff. So don't look for any kind of interpretation in the production logging from this, right? Okay, we talked about this tool already. Go. Okay, we have a tool called a noise tool, and a noise tool is all a noise tool is a microphone listening, right? It's a microphone with a broad band, a broad frequency band that just listens to noise. And noise has certain characteristics. I mean, if you're a guy banging a stereo, you hear the low frequency, you hear the high frequency. Similarly, fluids in a borehole have specific frequency spectrums. So you can distinguish between different types of noises, whether noise is coming, whether it flows from a formation, whether it flows from perforations, whether it flows from a leak through a casing, whether it's coming from a packer leak, etc., right? So there's very sophisticated tools on the market that sees a broad band, and there's a special tool made by unfortunately by a Russian company that can see 12 feet behind the formation. We were actually linking up with that company, but there has history now to the political situation. So the noise tools can actually look for leaks, can look for noise and stuff. So it's, as the word says, it just listens, right? Okay, the two things you have to remember here. The noise tool measures amplitude and frequency. The amplitude is a function of the different pressure and the fluid type, okay? So if you look at the amplitude, you can now tell pressure isn't a big thing, but you can now tell it's oil, water, gas. The frequency tells you the aperture size, just like somebody whistling, somebody blowing a whistle, or something coming through a very big orifice. The frequency will be quite different. So you can have an idea, not an actual measurement. You can have an idea whether this flow is going through something that's very small or is going through something very big. So these are some of the applications of it. And I'll be straight and honest with you. What we've done in Trinidad, a noise log has been used just to, we call it a leak log, to find leaks in the casing, leaks in the pipe, by just running the log and listening to what it is. It's just measuring. It's like taking your air, to use a raw analogy, and put it downhole, or taking a microphone and put it down. You hear the word hydrophone. All a hydrophone is a microphone that can work in a fluid. That's why it's called a hydrophone. So if you mess with seismics, we realize that you use hydrophones when you're pulling this thing in the water and all over the place. So. Okay, so here we are. We're talking about all the tools here. So what is done here now? The tools are actually hooked up like that. Each one is joined to one another. So you have here all the tools joined to one another here. The tools are actually run. We use the word centralized. These are things here, these things here, and this one here. They open or close depending on the diameter of the hole. So the tool is centralized here, running in there, and you have each one of these here inside. So you will hear people talk about what's the production logging string I'm running, or what you run there. And this is what you will normally hear. Okay, we're running the spinner normally goes at the bottom here. You have a density, you have a capacitance, and you have and so on and so on. You have this exact thing in there. So this is what will actually be run into the hole. And I said every one of these making a measurement is sent up hole, like we talked about in the first few slides, where you have digital measurement made. The analog is converted to digital, and then comes up hole, and we do the reverse. We take the digital measurement and we make what we call an actual log, right? Okay, any questions so far? Good. Okay, this here is a summary of what we just said here. Spinner will give you a velocity. The fluid density obviously measures the fluid density. Dielectric measures the capacitance with type of fluids. So these two will give you your density. The temperature, we talk about it. Pressure by the quartz gauge. And these two for correlation. Noise for your leaks right there. Their application, they noise are using production logging, but in my experience, the noise logging is to actually look for leaks, not adding anything to production logging. Okay. Okay, everything clear so far? Okay, a bit on the procedure. Those of you who in industry who actually go to work in production logging, you know, today there are procedures in doing everything, right? So I just run through. So you have here depth control on top here, and what is done here? The logs are made with the well shutting and the well flowing at different rates. Okay, you have the run there well shutting. In other words, you're making logging runs at different logging speeds, and that's actually done to calibrate. We might talk about the spinner, where the spinner measures revs per second. The revs per second is converted to feet per minute. Logging these different rates here allows you to do that. So you will also hear that terminology. We have to make multiple runs, calibrate the spinner. What you're doing there is trying to take a revs per second and converting it to feet per minute. So it's not like OpenOLog or a case tool cement quality evaluation where you make one run and they come out. You have to make multiple passes to do. What I'm getting here is that the production logging takes time. It generally takes a day. We just did a log for one company. It took I think we were up for 48 hours. Excuse me. Right, so there's a special procedure. If you want to go for an SIP or something like that, you have to make multiple flow rates where you put pressure against your rates here, and you're able to get your SIP done. Okay, but basically, what you're doing there is making multiple runs in the hole up, what you call logging up and logging down. You'll hear the word used. You're making up passes and down passes. It means we're running the tool down into the well, making it right to back out, making another measurement, and we're doing it at multiple speeds. If you want sophisticated interpretation, you have to now flow the well at different rates. So you have here, this well is flow at 10, 20, 30, 40 million, and it's run to make runs at 30, 60, and 90 feet a minute. Okay, that's basically what the operations is like. Okay, let's go into how many things we talk about now. You will hear the terminology, the hold up in the well, what to hold up in the well. My analogy for that is a bit silly, right? It is like looking at a pizza that's cut in slices. So if you take a slice of this well here and look down at it, you can separate it into 3 different pieces here, like so, like a slice of pizza here. And you have here what you call the hold up, and the hold up is a fraction of that liquid that occupies the space in there. So if you say my hold up of my water is 30% at this depth, it means at this depth, 30% of that cross-sectional area is occupied by water. Obviously, the sum of the hold up of gas, water, and oil is equal to 1. So one of the things you will hear a lot in production logging is hold up, right? And hold up is far different to water cut. Those are 2 completely different things. Water cut is you talk about something on surface. Hold up is a measurement downhole. It's done by the production logging. That's telling you if it's water hold up, what percentage of that cross-sectional area is occupied by water. If you talk about gas hold up, it's similarly, or oil up, the sum of the 3 has to be equal to 1. Okay, let's talk a bit about the interpretation. Now you can go into what I call a linear regression type of interpretation, where you solve a series of equations and in sequence, and you end up with how much water, oil, or gas that you're getting, and you know exactly what you have. The 2 very popular programs in the market. One is called Plato, is one we use, and one is called Kappa. And what they are based on is using statistical modeling, right? Something called global analysis. So what they do here is exactly what the sentence says. If you remember the sentence, they're basically solving all equations simultaneously. So in other words, you have a series of inputs, you have a series of measurements. You have a series of responses and you have an answer. So it's like writing a matrix like a V=IR, and you're solving for it. So you're looking for the best fit of the amount of oil, water, and the gas that you have in there, right? What is most important here, it solves the equation that best fits the flow profile and the input data. Well, what do I mean by that, right? I mean, what we do here is we calculate the amount of, this is water, this is the amount of oil. And what the program does now, it tries to recreate what a log response would be like. So if your log response, the measurement was this blue line here, and this is what you calculate here. It does an inverse matrix and then calculate what the value should be. The red here should be what it does. So it's telling you when these two have a good overlay, this model here is correct. Okay. And what it does, it measures something called incoherence. Incoherence is the sum of the errors of all these things. Okay. So without getting into the real mathematics of the thing works, what to remember there is Plato or Plato uses what we call global optimization. Kappa uses local optimization. Plato, what you do is you're taking the response of the entire curve and matching it to the entire thing. Kappa does point-to-point stuff, right? I'm not saying one is better than the other one, but those are the two. But if you're going into the industry and you're going into production logging, no one is doing linear regression, trying to solve one equation and going to another. In other words, I'm calculating the slip velocity, I'm calculating the hold up, I'm calculating the apparent velocity, and so on and so on. No, that's not done again. You take all the data and the program is doing to this field. The analysis is done where the log analysis is a guide the program. It's big, all the mathematics behind of it. And that's what you do. I know Stephen must be laughing. We've been doing interpretation like this for the last 2 weeks, right? Because it takes a little while to get it done. Okay, so here we go. So this is what it looks like as incoherence, and this is like what I just talked about here. You see here, you have a blue curve and a red curve. Great. When these two curves overlay one another, it tells you that this model here is correct. If you had a big discrepancy between these two here, it tells you this is wrong. So it means the analyst is inputting something wrong or something is wrong with the model. So what global optimization type of measurement gives you? It gives you, to use your own word, the correctness of your analysis. In other words, when you do a normal sequential type equation stuff, you get an answer. Okay, you don't know if the answer is right or wrong. In global optimization, you know exactly what your error is like, or how I don't know if it's wrong with inverted commas, how correct your answer is. So don't try running away from that kind of measurement, right? That is the way most programs are working today in terms of taking all the measurements. And now, having said that, if you want to be trained properly in production logging, it's good to understand the basic equations. Okay, so you can always go back to that, go back to your your equation, and you understand what is going on. But at the end of the day, this is what the programs out there. You'll find nobody doing this sequential type equation solving. Okay, and the interpretation comes out like this here. This is what we actually get. What I showed you before. It will give you the volumes, it'll give you the production. So you're seeing here, this is telling you, this is my depth here. Okay, this is telling you my volume. So I'm saying I'm getting this bit of gas from there, and then I get a big increase in here. I'm getting my here, this is the same thing there, and then you're getting your oil from across it. Okay, so this is the total flow rate here. This would be the contributions, each one of these. So that is the interpretation here. To my set, it converts downhole to surface rates. Okay, let's let some real log examples. If you want any questions here before we really go into real examples, right? In terms of the tool theory, in terms of the we'll not go much into the actual Plato. I'll just show you the output of what it actually gives. Are you okay?
So, Russell, I have a question. Hamid here. So
Yeah.
you know, so you mentioned with Plato it takes all the information that you input. So how does an analyst determine what might be a wrong input?
Okay. What you have there is you have you more or less telling the computer, you have to put a model there, right? You have to choose first. The model is either oil, water, gas. So you tell the system, okay, oil, water, or gas. And then you take the measurements and you have to take the velocity there. I don't want to go into much detail. And you have to actually tell the system where you have flow, where you don't have flow, where you have production or production. So it takes all of that. You have to enter certain things, pipe size and whatever, things like that. And then it makes a measurement of the incoherence. And the incoherence is a measurement. I'm not sure if I have it on one of these tracks here, right? Here we go, here. This measurement here, this here, see here, you have material balance, you have tools in it. So it tells you what my error is like here. This is worse. So if one of these things comes out way outside here, something's wrong, okay? So this here, in this incoherence, is the sum of the errors of each one of these measurements of these logs across. This is sum of two. And it's telling you here which one is coming from. So if you know, you have green here now, so you have slip velocity. Slip velocity is the velocity between the happy phase and the light phase, okay? If you go here now to material balance, you have a problem because the sum of what is going, what's coming from below should be what's on the top, So it means you have some wrong in the model. So this here is your actual check. You have two checks. The overlay of the curves in one another and the errors here, that is this not very large. Those are the two things that you actually check. So if you, for example, in this log here, you see here it's not looking too, but if the entire log was outside, if this red curve was constantly outside here like so, you know this is wrong, okay? So you're looking for something with a close overlay here like you see, okay? I think
and in terms of based on experience, what is good enough? What kind of coherence do you look for? How close should be the curves before you're happy with it?
You want it to be of this kind of value under 2000, but all depends on the quality of your data as well. Depends a lot on it. We do a lot of filtering to try to get it to as best as we can. Sometimes you have sometimes you have an answer where the model is not fitting well, but you can do that. You can say, for example, we're working a well here right now that has injection, and the model is not handling it very well. But we know, okay, that is wrong. The model is not just correct. For example, you may have downflow, or you may have water circulating, and the model is not accounting for that. So you have to come back to basics. That's why to understand what is this tool telling me. So this does not take away the human interface of understanding what is going on there. You're not going to just dump these into the machine, last files, and this thing's going to come out. There's a lot of thought into what comes out in there. But for example, if you look at here, you see here is very low. You see the good overlay you have in there. So you know that there. Put some confidence in that. Look at that. I believe that looks good, right? The other one I showed you here, this here is a cross.
This is perfect.
You see that? This is perfect. You want that. You aim for this, but sometimes you don't get it. Sometimes you can't get it. One is the data acquisition, and two is the model doesn't fit correctly. That's it. Because you have to tell the computer a lot of things. You have to tell the machine, I'm getting flow from here, I have down flow from here, I have up flow from there, I have cross flow here, I have production here, I have production here. So there's a lot of guiding you have to do to the system.
Right. So the analyst has to put in that type of information. You just put in information that
it's not automated.
Information you get from the surface, PBT data.
That's
you
right.
actually have to do some interpretation.
Yes, you have to enter like the gas gravity, you have to enter water salinity, you have to enter well deviation, you have to enter quite a few things, right? And you have to use the input data to tell the computer what exactly was doing. It's not doing. Plato is a huge mathematical machine, if you tell me, right? And you have to guide it. It's a great mathematical machine, solving equations, but there's no great intelligence in there, right? It's going to give you a mathematically correct thing, but it's not technically correct. In other words, it may show you somewhere where water is coming from, and your logs are saying, no way. For example, if your density log is reading 1 point naught, and it's showing you getting gas coming from there, you know something's wrong. So it doesn't take away from the analyst having to look at his data and seeing, hey, what am I inputting here wrong? The analyst has to input certain things. It's GIGO, right? Garbage in, garbage out, right? Definitely something like that, you'll get, right? So it's a tremendous amount of guiding it. A tremendous amount of lots of people do not like the program because the program does a lot of things here, a lot of mathematics behind it that you have no control on, right? So it has the equation, but it has constraints. Certain constraints that are written in there that you can't change. Material balance is one of them. The sum of the three holdups, why water, while oil or gas is equal to 1. You can't change that. Now, if you're doing manual thing, you can go ahead and tweak that, right? Plato or Kappa does not allow you to do things like that.
It's like some universal constraints.
It's constraints. Yeah, you have constraints and you have
I can't imagine you'd want it not to be equal to 1, but I'm not.
Yeah.
I don't know it well enough to know. And then in terms of the technology and the with respect to artificial intelligence, self-learning, are you aware if any of that is happening in log interpretation?
Well, I'm so glad you asked that. My son-in-law is a lawyer showed me an article recently about automated well log interpretation, and I had about to have another laugh, right? Now, Stephen, correct me wrong. He said somebody, I think, presented a paper recently on it in one of the SP conferences. Some kind of automated open hole logging interpretation. I mean, I remember many years ago in summer that was actually tried, but I don't know if they dropped it and it never worked. Where you was fully automated, but I don't know where is it today. But I know there are lots of things that people are doing now that are fully automated, and the industry is going there. I'm sure in a few years we may not be around for that, but it's probably going in that direction. You got powerful computers, you got logics, you got program that you can build some kind of intelligence into the thing.
In terms of an interpretation, Hamid, we're not quite there yet. What people are working on is machine learning for bulk data. So Russell and I would look at a log one at a time and be quite overwhelmed with the volume of data for one job. So what they're trying to do is trend hundreds of jobs together and then use that statistical trend to fill in gaps in older well logs, or sometimes you have a missing gap in data or bad data or tool malfunction. They have found pretty good fit with AI for filling in the blanks, in other words. But in terms of interpretation, you still need a lot of the analyst input to drive the interpretation direction it's going. But that chunk database that you can trend values with could end up being very helpful, because if, let's say, for example, Russell and I had 12 other wells that did that injection response we're working on right now, we could with a little more certainty say what we think is the answer. But right now we're sort of in a bubble. We don't know truly what is happening downhole because we don't have any reference. So that's where the AI is really coming in terms of generating invisible data there.
I get it. But I think it's only a matter of time.
Well, my son actually told me, he said it is very fast in the legal industry. He said he's seen lots of documents where the legal world is getting there. So, I mean, his take was probably won't have a job somewhere down the road, right? But I think that's far
absolutely
down the road. There's far down the road there. I mean, you have automated platforms these days, where there's no one on unmanned platforms. Nobody's over there. Production platforms.
Well, I know there are two things. One is data management. You have all this amount of data, and how do you filter it and then pass it on to people to then do an interpretation. So I know that filtering part of it, but the AI to me is where it's the self-learning part of it is where I think it's pretty interesting and the impact it might have on things like this. So Anyway, so
I think some Plato is very getting close to it. You can take some like Plato and write some kind of
well, that's what I got when you were talking about it. If it's
It can work,
taken,
yeah, it can work, It can work with some.
yeah, because if it's
Yeah,
taken and trying
yeah,
to ensure
yeah,
that you have
yeah.
everything adds up,
Yeah, that's
you know,
right. Yeah,
from
yeah.
different sources. To me,
Yeah.
that is what it's trying to do.
Oh yeah, oh yeah. It's a close. It's the closest I've
Mhm,
seen to what we're talking about here, where it's actually taking away a lot of the stuff from it, and it moves away totally from linear regression. And nobody wants to do that again. So if you what I'm trying to students, when people hear the word global optimization, they don't want to use it. But most of the software that I've used, if it was in Schlumberger, I think Elan is now Petrol or something, right? And it is the same kind of principle, right? Of trying to use all the data at one time to solve the problem instead of sequential solving of the equations. And
Yeah,
they get better data than that. I mean, some of the programs that is in Opal can actually score data to help you with it.
Yeah. Thanks so much.
Not a problem. All right, everybody okay to go into examples so we understand how tools work, what we're looking at, because from now on I'll just show you some examples. Okay. So any questions so far? Okay, let's look at what we have here. We call this water injection well. Water injection means pumping water down this tubing, flooding the formation. So remember I said the birth certificate of a well, I'm laughing again, is the open hole gamma. So every time a log is run, you have the gamma of the open hole and then the gamma of the tool that you're running. It's put side by side. It's as if you're checking a log. Check that this looks just like means it is at the same depth of this. So this is saying, I will show you here my sand here, so it should seat exactly that. So you know you get it. Then you have the temperature log, and the temperature is run like that. Remember what we said. What's the temperature measured? Temperature is measuring temperature of the well, as the word says, but it's measuring also what changes in the well. So when you see here, you're pumping water into this reservoir here. This is the interpretation here. You can see it's showing here, yes, the water is going down here, so the water is coming side up here. It's a very, very simple example. What happens here? You go back to zero. The way you interpret temperature logs is you first of all establish what is your geothermal gradient. In other words, this here looks like you. So you draw a line across here that establish geothermal gradient. And any deviations from the geothermal gradient is evidence of flow downward. So it means you could have a heating effect, you could have a cooling effect. Okay, so that's the way you will interpret it. So you see here, this here will not be geothermal here because you're pumping down here, so the temperature will be changing. But all the water goes in here, so your well is now trying to get back to geothermal and here. So your line will be run like that, you know, and you have this here, this surface here, and these here, evidence of your flow. In production logging, in Plato has a modeling section where you can actually use the temperature log to model flow. It's very complicated because it requires thermal conductivity for a lot of things that we don't know. I've tried it once and it's extremely difficult, not to run, but to have the correct thermal conductivities for everything in there. You need to know the thermal conductivity of rock, the thermal communication, the thermal conductivity of cement, and so on, right? But it does exist. Okay, here we go now. What is this? This is a comparison of temperature and spinner. Temperature measures the temperature of the well. It says, what is spinner measure? Spinner is measuring the rate at which the well is flowing. Remember we said we have in there a measurement of impeller turning at the speed of the fluid. And then we take that and we convert it to feet per second. So what we have here, this track here, pretty colors here, we might say there be multiple trips. No, these are the multiple logging runs here. These are the temperature changes in, right? So see these here, what is this telling me, right? Every change in the spinner measurement is an indication of flow. Flow at this point here, flow at this point here. This here is your interpretation here. You can see here, this change in the slope here corresponds to the here, this other change corresponds to here. Now you would see water and oil. This obviously didn't come from these measurements. This is from some other measurement in here. But that what I showed you there is the way you interpret the log. Okay. So if I had to do an interpretation there, this is a straight line. There's no flow. Where the word you use here is no, it doesn't produce from here. I have production from here, and you can see this in here is telling me that the reservoir from there to there, which is this one here, these are the curves here, that you have production from here, no production from here, so on here, and so on and so on, no production from the bottom here. So generally, or when you interpret the spin or any log here, you put your perforations to the side of the thing here, and you're looking at the actual perforations here against it. What are you seeing there? The top perforations are not flowing. There's none here, there's none here at all. Perforations start way there. So immediately, you have a problem there. You see what you've just found out here, you've spent money to do all these perforations here, and you're seeing here, this is a straight line here. From here to here, not seeing much perforating. We're just seeing part of this here and part of the top here. So you perforated all this of the reservoir, and then you're not flowing. And that brings you back now, you have to go back to your open logs, you have to go to your completion design, you have to go back to all kinds of things. But you've seen from the production log why your well is not producing the way it should. And this is a very, very simple example of what you use the production log for. Okay, let's get to something a little more complicated now. This here is your velocity. We call it VP, the parent fluid velocity here, okay? So you have the fluid velocity minus 50 to 50. Minus will mean that the flow is going in the opposite direction, plus is the flow is going in the correct direction. So what do you have here? See here, it goes behind here and it's back positive. So what is this telling you here, right? This is what we call cross flow, when fluid goes back down, so it goes negative here. So it means you have a production from this depth here, from 12,232, but some of it is going uphill by the positive value, and some of it is going downhill. Exactly what I was talking about in terms of a well heaving, right? Something is coursing here to go back here. So when you interpret the velocity here, you have to be careful of your polarity, because negative means you're flowing down, positive means you're flowing up. And this here would be the actual acquisition data. This here is your interpretation. You see, yeah, comes back here. What's that telling me here? From this depth here, 12,200 and about more than 50, you have no flow, right? So you have no flow here. You have flow coming down the pipe into here and flowing up. So if you had sands here, it'll be telling you that some of this is flowing into the reservoir back here, and some of it is going back up hole. So it's just, you realize they are very, very simple measurements, very, very simple. It's just applying it to what you are, to the geometry of the well, okay? And I stress again, when you're looking at is velocity, be sure you look at polarity, because you have to be sure what is negative, what is positive, what is going uphole, and what is going out. Now, if you didn't look there, you would say, okay, I got no flow here, but going uphole, that is still uphole, but less than here. No, polarity says, excuse me, polarity tells you this is going downhill. Okay, another very complicated one. Now, I'm sure you can do this already by yourself, right? You establish the zero line here, which is negative, which is positive here, right? So what are you seeing here? From the bottom here, you go positive. It means you have flow from here. So some of the flow goes upward, some goes down. So it's increasing. So it's increasing value here. It gets to a value here, and you start to lose fluids here again. You get negative flow in there. All the flow is lost in there. So see exactly what can happen down. Okay, you think everything is great with the reservoir, but depending on your pressure regime down, one reservoir having a completely different pressure here, one reservoir being depleted, you can have all kinds of complicated flow downhole. As I said before, there are no measurements on surface that can actually give you this downhole picture.
And Russell, just to share, So you would expect then that the measurement on the surface will be 0.
Yeah, exactly. And you wonder what's going on. And you could postulate 2,000 different things, eh? You can go from I'll tell you the first thing people think. If the new well perforations are not there, perforations of depth. Okay, that's the first thing you start to think. And I tell you something, like for example, when a TCP is job, the first thing I checked, if something is not going well, let's check the correlation. Okay, we're good on that. And then we start to look for where the issue is. Some of the issues sometimes you perforate overbalanced. So you kill the well, which you don't want to do. Sometimes the reservoir is tight, you didn't check that it is, and things like that. Eh? But down the road, in a well that is now changing from oil to water, it's a different problem. Going into, do I have water breakthrough? Is the top sand not flowing, and the various things like that. So depending on the age of the well, the way you approach it is quite different. The way you approach the production logging is quite different. Lots of people, obviously have money, some they don't do it again, not in this era. They would run a production log as soon as the well is cleaned up and go in production. So have what you call a base log. And then they do what you call time-lapse logging. So they run a production log in 2 years from now, 4 years from now, and they can actually look at actually what they are having. When I worked for Petrobras in Brazil, when I worked for Schlumberger for Petrobras, they actually used to do a lot of what we call time-lapse logging in pulse nutrient decay and in this kind of thing. So they're quickly able to understand exactly what is going on. The problem we have in Trinidad is that the well starts to make water, and by the time the engineer gets the approval from his boss, the production login, the well's making 100% water. So that defeats the whole thing. I always tell people, run production log as soon as you show that the well is not doing it. So it starts to make 100 barrels of water to the next week is 200 and 300 and 400. Do not wait till it's 100% that you can't do anything. That is the issue I've had with lots of people trying to get correct data from production logging. Right. Okay, so we see this again. This the message I want to leave here is when you're doing the spinner velocity interpretation, establish your zero line, what is zero flow, and show what is negative flow, show is positive flow, and you know negative flow is flow downhole, zero is no flow, positive flow is flow coming up, right? I think we beat that a bit, right? Okay. Look at the way, this is the way acquisition data actually looks like. So after you run a log, this is what you would get. This thing comes to your desk. Okay, this thing is at the thing. If we look at this here now, let's say this piece of paper comes to you midnight, you got no computer and that kind of thing. What are the things that you're seeing, right? See here your temperature log, you're not seeing anything great here. See here your density log. Look at the density log here. The density reads 1 here and then goes down to here. Capacitance goes to this volume here. So what you're telling yourself here is that I have water at the bottom here. I have a mixture here of oil and water, and then I go to a big column of gas. Capacitance is showing the same thing here. Capacitance reads low for water here. You get into the mixture here, and then you go to a column of gas. So that is what we call a quick look type of interpretation. I've not mentioned quantities there, but I've used the log there for that. You look at the spinner here, right? This is my spinner, so I measuring flow. You see the gradual increase in here, and you see when you start to get your gas column, how you're increasing here. What you can also say here is after this depth, I do not see any increases. So I don't know what's going on with these reservoirs. It's top up here. So quickly looking at the log tells you, okay, I got water here, I got some gas coming in here, I got mixed in here, but also my top of my flow is somewhere here. You can say with some confidence quickly before you go into that. So having that, you go into your production logging analysis, your Plato, and that is behind your head. You're now going to tell the machine, this is what I have at the bottom, this is what I have flow there, and the machine is going to take that and solve that model and give you a coherence to see how correct in inverted commas your model is. That's exactly the way things work. And I'm sure somebody can write that machine language. Now, what you would have done here in the interpretation here, you might said you take the spinner data in revs per second and you convert it into velocity. So see, this is what Plato would have done. Taking this here and it did exactly what we just said together. The top here, you've got no flow, but you have flow increasing from the bottom here, flow in there, no flow here, some flow in here, none in the section here, and then flow increases in here, increases in there, and at the top here you have flow. So your visual interpretation, your quick look interpretation has to guide everything here. This is not saying anything different that we just talked about, right? Any questions on that? Okay, and then this is what Plato does for you, right? Here we go. This is Mr. Plato, right? So you see here, this is your inference here, right? So the model is saying this is not so good. That's very correct. Look at the separation here. Model is not very correct in here, right? It's having difficulty trying to solve this, okay? Because your overlay is not good. But as you get further up the well, here, you have confidence in these answers. You see where incoherence goes, almost to zero, okay? So you're pretty certain up to here, your model is correct. And why is your model not correct in there? You understand? The program has difficulty when you have a mixture of oil and water. If you have a single phase, one of the here is okay. So you see here, you have all gas in there, it's okay. At the bottom here, you see the incurrence is gone there. You have all water here. This is your hold up, right? You hold up, what I said hold up is a measurement of the fraction of the fluids of the kind you hold. So blue is water, red is gas. So at this point here, you see your hold up of water is almost 100%. As you get up here, there's no blue, so your gas is okay. Here you have various amounts here. You can see it looks like about 30%, here maybe 50%, and so on, right? So that's what the hold up looks like. So you have your incoherence, your hold ups, your total flow, and here you have your computed values. In other words, the values that Plato has made through the inverse matrix against your acquisition data, okay? What you ideally want to see is you want to see an overlay of this thing here. And this here is telling you, okay, it's not handling the model very well. So this may not be totally correct, okay? But from here, I'm pretty certain that is totally correct. Right. Okay. Here we go. Okay, any questions on that? That's exactly what Plato is, where I guess anybody use Kappa, but Kappa would give that same kind of answer, I'm guessing.
Russell, I mean, not to, so the lower part of it seems to be in terms of what the interpretation is. But what I'm curious about is that you have water being produced, but then you have a total gas flow coming up. What happens to the water?
Yeah,
if it's coming into the wellbore?
It's still coming up whole here. It's still coming up all here, but your hold up the percentage is so high. So in other words, here you probably have 90% gas and 10% on top of here, right? But it's still coming to surface. Okay, it's probably much lower here behind here somewhere. Okay? So you're actually getting both of them. What as we go further on, we have what we call in deviated wells, you have water on the low side of the hole. I'm not sure what is the problem in there. That sometimes with a normal tool, when I said a tool is run centralized. When you have water on a deviated well, a low side of the tool, a normal tool will not store it. I'll explain that basically. We did a well for one of the operators recently where you have the well is making, see if you correct me if I'm wrong again, the well is making about I think 150 barrels and expected 500 barrels. When we ran the log, we found that we have water coming up, water recirculating across the perfs, and that's killing the flow. Now, they were talking about fracking the well and all kinds of things. Now, when we showed them, they were shocked. So they changed the total interpretation completely, because you judge against surface, open no logs and saying this was, and when they saw what we showed them, it was a totally different, shocking picture, I would say. So a lot of times you have an interpretation of what may be going on in the well, and if you don't have a production logging giving you a full picture, image of downhole, you're not anyway told.
Yeah, you could get it very wrong.
Oh yeah, oh yeah, oh yeah. And you see
And
what you
then
can
you can
spend
plan a
money.
remedial type
Yeah,
work and spend a whole
yeah,
bunch of money and make it worse
yeah,
or not get back your,
yeah.
a return on your investment. Yeah,
To
absolutely.
give you what a fiasco that could have been. When you frack a well that has a water leg, you know what you're doing? You're fracking into the water. So
Oh, sure. Yeah, absolutely.
you've now killed the entire, you've lost the well, right? It's done, you're going to
You've
go back
lost
on.
the entire world. Yeah.
Yeah, so that was so that production log was some good information. Then we're like, listen, what we're doing is wrong, wrong. All right, okay, let's go here now. Okay, people, now this here is a question to everyone here. We have here the temperature log. So temperature log is here. We have the pressure line showing here. We have the density log here, and we have the capacitance. And you have to say where the water is coming from, right? We'll have to answer the question, right? So remember what I said. The way you interpret temperature logs is you try to find some kind of geothermal gradient there, and any deviations from the geothermal gradient is evidence of some kind of flow happening downhole. This is quick and dirty without even going to any kind of production logging. Sometimes you send offshore on a website, and you have to run a log, and you have to now set a plug immediately. That's immediately you have to get an answer. So you do not have days to make an interpretation. So you have to go on what the data is showing you. Data will take us at least for full interpretation, depending weeks sometimes, days sometimes. But if you want a quick interpretation, you have to go back to basics. So do not only depend on your computer processed interpretation. So now remember what you're seeing, right? When you go there, this here was the actual computer processed interpretation. What is it showing me here, right? This is my hold up here, and this here is actually where. So you see actually where most of the water is coming from, right? And if you go right back here, you see where the temperature anomaly is here, right there, okay? So here you have water coming from below, but you have a lot of the water in the middle of the person here. So what do you do? Yeah, question is there. I have some gas coming from the bottom here. I have some gas coming from here. I have to decide whether I would put my bridge plug here, lose this gas, but get rid of this water, or put my bridge plug sometime here, get rid of this gas, this one, but kill all the water. So those are the economic decisions you have to make, but you can only make it after you look at the production logging that gives you. So you have up there, you have your water you have your water in barrels, you have your gas in your millions. So you know exactly what I can tolerate, what I can lose, and so on and so on. Some people may say, okay, place to put the plug is here. I'm going to give up all this water, but this gas, but I'm going to kill all this water, but I'm going to get rid of this amount here, but I'm going to this gas, right? If it was my well, this is where it's going, right there, okay? And because I'm keeping this gas in there, okay? So you see exactly how we can use the log. Now, if you did not have this computer process interpretation, you can see here quickly here, look what the density changes here. The big change in the density is there, which corresponds to somewhere on top of there. So using here instead of the plug, you may not be very, very wrong, right? You're going from water line here to somewhere in here. And you have the temperature effects right in this area here. Okay. So this is showing how you can use the acquisition data against the process data. So they don't get me wrong that you have to always wait on this pretty thing that Stephen Russ is going to do. You can make a lot of decisions from your, but if you want volumes, you have to go here. Okay. Okay, this looks like a much easier one here. This here is your, you see, again, I always make the analogy of temperature with SP log. Most people in open log, you don't want to hear about an SP log. I'm old fashioned. An SP log and a temperature log, I put a lot of emphasis on. You can see the temperature log here is trying to get back to geothermal, but you have anomalies in here, right? You have one anomaly here, you have another one here. So you have two places of it. So you see here, look at the spinner. You see you have flow increase. And there you have the density log shows you here, water into there, capacitance in here, the electric is the same thing in there. So you know immediately you have some problems in there, right? Problems inside. inside of here. Okay, you can see a small change in the capacitance across it. So if this here is gas here and you have a change here, you tell yourself, I should be getting some water here. You see where your temperature log actually shows that. So there's a lot of information, qualitative information, and looking at the temperature log gives you no calculations, but it helps you with the answer, with formulating a good answer. Okay, in terms of a quick look answer, we're trying to make some decision. Okay, and you see what the answer is there, right? Exactly, I said, you see there, you have water coming from inside of here and some from the bottom. Now, this is a difficult call because you have a lot of gas coming from the bottom and you have water in the middle here, right? So this, if I remember correctly, this was a horizontal well. I'm not sure what they actually did with this here. They just carry on, or they were able to sleeve this or some things, I don't know. But you see the kind of issues you can have here. You would not expect water to be in the middle of these zones in here, but without my fancy interpretation, you can see here the temperature anomaly there, and you can see the change in the, you can see here the density did not show much change. Why is the density not showing much change? Because the differences here is not very much, but the capacitance is showing the big change in here, right? Remember, the capacitance is what we call the water holder tool, okay? It helps you distinguish water a lot more. See the change here, but you're not seeing any change there. So with the capacitance and the temperature, you get it. Obviously, if you have your process interpretation, you're good to go. Okay. Okay, you see here we have the we sometimes with Steven's help we're able to put all kinds of open hole logs and things like that. I don't know all these tricks. You can actually put the open hole logs here and actually see what is going on here. So that actually looks a little wet to me, the resistivity here. Your pistons look like these two here across there. Okay, this here is your noise. What did I say the noise log measures? The noise log is listening down hole, just listening. Okay, so what do you do? This blue thing here is a spectrum. The spectrum is just trying to take the measurements and making a picture of it in terms of the amplitude. So most of the applications we've had on the East Coast is leaking gas lift mandrels. So we go at each mandrel and make these measurements. So we are listening, okay? So see, you go at this point here and your noise increases, right? And you can see here, you get an increase here on your measurements as well. We're able to make some colors in here, but here, you see, we see exactly at this point, you have a noise coming from this here. So they had a big program out there changing the gas lift mandrels. We're running noise logs, and they actually call leak logs. And leak logs, you run temperature, and you run a spinner, and you run the Stephen, I don't think I forget. Do you run anything else?
No, I think I think the main thing is the spinner temperature
yeah,
and the noise too.
Yeah, right. Okay, good. So you see what you do there, and you just go in down hole and listening. As I said, just a listening device, and you can actually get in that. Okay. Okay. Want to give you all. If this here is a real life P2 example of a measurement, right? So what we have here on the left-hand side here, we have the perforations here, we have your CCL. We have here a temperature log, we have here the pressure in blue, we have our green is our density, and we have here our velocity. Now, this is simple. If I ask you all, if you're willing to take a shot of it, where the oil, the water, and the gas coming from. And this is as basic as we can get here. What you're doing here is taking your basic information I gave you. What is the density measure? Density of water is different to the density of gas. The velocity would change in gas, okay? The temperature would show anomalies. When you get gas entry, you have a bigger cooling effect. We talk about the Joule-Thomson effect. So what would you say? Would you all willing to answer this, or you want me to show you the answer? Now, but what you have to do there is not a guessing game. You have to take, I said in temperature log, where you interpret a temperature log is you establish some kind of geothermal gradient and you look for deviations from line. So you can see from here, which is the top of the perf here. That's the perf here. Lines are very nice. You have all kinds of deviations here. What I said is that the gas effect, the cooling effect is greater in gas. You generally get some kind of heating effect when you get into the water or oil, and you have here density differences. We can look at it for a few minutes, and if you get an answer in your mind, and just explain the answer on the next one. I'll look at the show every day, what America says, right? I don't know if anybody look at that, right? Anybody willing to give an answer? Even not you and Ahmed.
Is the depth of the bottom depth of the gas is approximately 7120 thereabouts, and the depth of the bottom of the oil, which would be the top of the water, is about 7170.
Okay, well, if I ask you, when I teach people, I tell them I give 2 questions in one. Why, right?
Why? But I'm seeing a reduction in density between about 7110 and 7120 thereabout. So I assume that's
Yeah.
a gas cap.
Yeah. What you're saying is correct. What you have to do is approach it with the 3 curves together, right? Like you see the temperature change here and the density change. You correlate in each one here, and you always get, because of the lightness of gas, you always get a bigger kick when you have a bigger change in the velocity when you have here. So you know this is where your gas comes in, right? So if you go here, what do you say? The answers are there. So you're more or less correct, right? So this here was the actual computer process interpretation. You have water at the bottom here with your density reading close there. Then you have your oil coming in here, and you have a gas at the top here. You see a big change in there. But again, not even using it, using basic principles that I've just talked about here. You can actually do an interpretation of these without the volumes. Okay, so you see how easy it is to do. And I tell you, it's not as easy as this, but this is a simple example to ensure that we understand exactly how do you use the actual data when you do not have the fancy computer processed interpretation. This ties in there, the oil ties in there. You can see your changes in there, right? You generally see a big change in the temperature and on the velocity whenever you have a gas entry. Any questions on this example? Good. Okay, I'll just go into horizontal. Why would it horizontal wells? Most of the wells that are not on land, most of the wells that have been drilled offshore are horizontal wells or heavily deviated wells. Now, what is the problem with this here? Right, this is looks like a snake, right? Now, remember what I said. The tools that we just talked about, they make measurements in the middle of the hole. So if I put a tool to make a measurement in here, it will not see this water here. If I put it here, it will not see this gas here. So what do you say? The conventional tools cannot be used in horizontal wells because they're making measurements in the middle of the hole. So there's a new generation of, not very new generation of tools, but is a generation of tools here that allows you to make measurements around the ball. Okay? They got various names for them. The ones we use are tools out of G-Sondex, they call maps multiple array tool. But regardless of the trade names, they all work with Schlumberger or whatever. They work exactly the same way. Instead of making measurements in the middle of the hole there, make measurements around the ball. So remember what is going to happen to you, right? When you have horizontal well, a heavy phase, the water or the oil is going to go at the bottom, the lighter phase is going to be at the top. So many measurements in the middle of the hole is going to miss what is on the top or what is on the bottom, right? Okay, that I explain that. Right? Okay. This is actually a picture of what actually happens in this is something called a flow loop, and if you all, I mean, everybody got the, I think there's one on YouTube where they actually take, they take a horizontal pipe and then it's transparent, and then they pumped gas and oil into it, and then they tilt the pipe, and it goes from vertical to 89 degrees, and they look at the way, the behavior of the fluids in there, and you'll be amazed, excuse me, when you get down below 65 degrees, what actually happens. It's a totally different picture. I always use the example of Maracas Beach on a rough day. It looks exactly like that. You have flow going up, flow going down, you have cross flow, you have all kinds of things. So a conventional measurement will never be able to analyze that kind of flow behavior. Okay, so forget about that. So what do we do? In a normal well that's vertical, a logging tool will just flow down the hill by gravity. There's not a problem in there. When the well becomes deviated, when the well becomes 65 degrees, 70 degrees at the horizontal there, it cannot go down. So there's the tools in the industry called tractor tools. So that's just like a tractor. What you do is you have here drive with orthogonal wheels in different directions here, right? You have one plate and one plate in here. And you hook the logging tool onto this. And these tools, these wheels are driven from surface. So they actually roll downhill like a tractor, because a normal tool will not go down a deviated well. So when you have a deviated well, you have the tools that are on a tractor. One of the companies working in Trinidad, I can't remember the name, but they got tractors and they specialize only in tractor measurements. Okay, so you can get tools down horizontal well, either in coil tubing or with tractor measurements. Tractor measurements are generally the preferred way because they're a lot cheaper than the other measurement in there. So if you have the word tractor, what it means in the logging world means that they have motors in this thing here, up in here, orthogonal wheels. Tools are hooked up onto this thing here, and these wheels are driven from surface, just drives the thing down the hill, down here. Actually, just to give you a little bit of history, those of you who look at the History Channel, when this technology came from when they decided to look inside of the pyramids, there were certain things that they wanted to look at. And they actually build something like this with a camera at the end of it. And they're able to go inside the pyramids in certain very small places where people could not see. The technology actually came from there, and the oil industry took it and made this very fancy today. Okay. How do these tools make measurements? Now, remember, I told you all that measurements are made in a conventional way in the middle of the hole. So, if you have a deviated well and you have what we call fluid segregation, heavy fluid on the low side, light on the other side, you will not see. So, what is made in the industry? Something called, you have some really funny names with laugh: rat and cat and sat. Rat was what we call a resistivity array tool. So on each one of these arms here, we have a resistivity measurement. So when you put this tool into the borehole, it makes a measurement of resistivity around the borehole. So obviously the resistivity of oil, water, and gas are different. So you'd see if this here is your well, these would see the top of the hole, this would see the middle of the hole, and these would see the bottom of the hole. If you run a conventional tool, it will see the middle of the hole, and the interpretation will be totally incorrect, right? It's called the rat resistivity array, right? Now, a little more laughing. Now, we call this SAT. The SAT is what we call a spinner array tool. I didn't mention that, but you have 12 resistivities across. Here you have 6 measurements, and the same design you have, the little impellers, you have spinners here around the borehole well here that actually turn depending on the fluids. Again, we'll give the velocity on the top, velocity in the middle, and velocity on the bottom. Why is this important? Obviously, the velocity of the gas here would be a lot higher than the velocity of the water here. What I mentioned before, remember I said, in a deviated well, you could have water going up the hole. If this is the well bore, right? Water goes up the hole, and then the water gets to the level where it loses energy. It comes back down the hole. It will not come back in the middle of the hole. It will now come back on the low side of the hole here, okay? So if you have a deviated well and you run middle, the tools that making the measurement, you will not see this water that is coming down here. So anytime you have a deviated well, you have problems of water flow. The RAT and the SAT are essential measurements to actually look at that. To what they will do, as I showed, they give you an actual image of the borehole. So you're actually looking at the borehole to see exactly what is going on in there. Third measurement is CAT that provides a capacitance measurement. It uses the same kind of, we have 12 sensors around here, and it's just making it's making the capacitance measurement of here around the board. So you have the RAT, the CAT, and the SAT. And all they're doing is, by design, they just have multiple measurements around the perimeter of the tool, and allows you to see the entire 360-degree picture of the actual wellbore in terms of the oil, water, and gas. Because they measure resistivity, they measure capacitance, and they measure flow. So using those three things, you can actually look at your wellbore and understand exactly what is going on in there. To give you an idea of the sensor size, this is my 25 cents piece here, and this here is the size of the sensor. So you see what they can actually measure. This is how they actually look like across on the these are the particular sensors here that make the measure there. And these springs here, they're moving in and out depending on the size of the bowl. So if the bowl becomes bigger, they'll go out. Smaller, they'll come back in and there. Okay, and this now will now give you a picture of what your tools will actually see. These here are the measurements they'll make on the outside here. If you had your conventional tool, it would be inside of here, and it's okay, I got all the oil, I'm good to go. But your other measurements will show I got gas on the top, oil on the water, oil in the middle. And this is just fluid segregation of the lighter phase being on the top, medium in there, and to down in the bottom. So you'd already miss all your water and wondering where is all this water coming. We'll have a reverse problem now. I have 1,000 barrels of water coming to the surface and I can't figure out where this is coming from because my conventional measurement is telling me I got oil. So you can run the log, you can do it in fancy interpretation, Plato, Kappa, whatever, in the conventional mode, and you will have a wrong answer because you have used the incorrect tool to try and model the actual flow that you have in downhole. This is a picture of actually what the tool would make. So you see, it's 1,000 words in there, right? So in terms of color here, it's too many colors somewhere. I think it's blue. This here would be your water. This here is looking at a slice of the well here, okay? So you're looking at here at this depth, 61, whatever it is, 61, 42, whatever here. So you're seeing on the lower side here, you have all water in here, and you have mixtures in here with some gas on the top. The center tool will just in the middle here, which will not see any tool. So we can actually, this is not Plato, this is some, I think this is category Stephen. This is what you actually see from the measurement, okay? Now this here looks very confusing, but this here is the interpretation from running the total maps tool, right? Don't worry, this here, from here to the corner here are the acquisition, don't worry about too much here. But you can see here, this here is giving you actual pictures of the wellbore. What's it telling you here? Okay, I'll tell you. This here, you can see on the low side of the hole, you can see the high side of the hole. So you can see at this step from 9675, I have water on one side, oil on the top, and I got oil gas on the top here. By playing with this here, you see 0 to 0.5 here. If you go on the other side, you can see from the low side of the hole to the middle of the hole. You can see from the middle of the hole to the high side of the hole. So you get a complete picture of the hole in terms of the colors in there. And these here, this here is the spinner measurements, the 6, this here is the 12 RAT measurements, and these are what I use. Plato has that as well. We use these measurements to actually make these things in here. Now this one here is your actually velocity profile. You have a profile across the borehole to see exactly what is going on. Where's your high velocity? Where's your low velocity? Come here now. This is exactly what I'm going to show you again, all right? So see here, 0 to 0.5, this tells you from the low side of the hole, middle of the hole, this is what I have. Up here, water in here. You can see here, see is negative. this value here, this is 0 here. So anything less than red in this here tells you it's negative. So it's telling you have water flowing down on the low side of the hole. So it gives you a complete picture. The low side of the hole, high side of the hole. It will calculate the volumes and everything for you and show you exactly what is going on in the reactor wellbore. Okay, this is look at the high side. You know, the high side, this is from the middle of the hole to the high side. It becomes red because on the high side you have all your gas. See you have here, you have negative velocities in here. Okay, so it tells you exactly where you have your high side, where you have low side, where you have the velocity. So in a divided well, you can get a complete picture of exactly what is going on. It's like taking a core sample of your production log, which is sounds stupid, but it's the analogy of a core in an open hole environment where you actually see the rock here and actually see like flow that's up and down hole. You can see here, this looks like mixture, right? You have a mixture on one side of it. This is one of the fancy interpretations. It's like it's getting really fancy. You can make a cutaway view, and a cutaway view you can see here. See actually here, flow coming up hole and flow going back down. So you can make all kinds of fancy analysis from that. I think the next one is the one I would like to look at. This gives you a profile of the actual well here. You can see here you have the mixture of oil and gas, and here you have all water. And this is the actual track of the well, showing the top of here, the heel, going to the toe down here. So you actually see where your water is actually. See that all your flow is coming here from this part of the well in here. You can make pictures like this. This can be rotated in different angles and get it in there. So the maps tools in a nutshell will give you a complete picture. You don't run maps in every well. It's an expensive business. The maps are run in horizontal and heavy deviated wells where you want to get a complete picture. If your well is not deviated, you can use your conventional measurements. You can do quick look interpolation by looking at your data. I want to stress on you, do not depend on that computer processing. Look at your data. Your data tells you a lot before you get into something first, right? Okay, in a nutshell, right? You have your flow. Generally, flow is 2 phases or 3 phases. In other words, you either got oil and water, oil and gas, so on and so on. You got 3 oil, water, and gas. And if you remember one thing from today, production log determines how much is coming from where. Conventional tools, I explained that is working very well when your well is vertical, it changes there. When your well is horizontal, you've got segregation, your gas is on the high side, your water is on the low side. You can use your maps. Maps gives you a complete picture of your borehole. There are ways of getting down in a well bore like this. It's called a tractor. Tractor just takes the tool down into the well and makes your measurements. Right. Well, I'm on the button. 2 hours. That's all I got. I hope Stephen is there because I'm tired. He will answer your questions.
Wow, that was awesome.
Yes, this was very nice. I will do that every year as long as I can do it because I enjoy doing it.
Yeah, that was great. So I don't know if these students, anybody has any questions for Russell. I don't know if the students are just blown away or.
So if you,
I just have one question.
Mhm.
I don't know. I hope it doesn't sound silly, but how do you flow a well and run a tool at the same time?
Yes, okay, that's a good question. In the logging industry, we have something called pressure control, and pressure control uses something seal. In other words, you have a cable going through a tube, and if my pressure is forced upon the area, you have the space between the cable and the flow tube is very small. We pump grease in there, and the grease holds the seal. That's one part. Then what you have to do, you have to compute how much weights you need to balance the pressure in there. So balance it by the weights you put on the tools. That's very good. We have a program called Stephen help me. Stephen?
Cerberus.
Cerberus, that's right. Thank you. Cerberus will now model the exact dynamics of the well. You put in all these things, there's all kind of friction factor, there's weights, and you will now change certain things, change tool size, tool weights, and put everything in there, and it will tell you very, very accurately how much weight you need, how far you can get down, if you need a tractor, and so on and so on. So just about every production log we do, we actually have to do that. So we can run production logs without that. One, pressure control on surface as a safety measurement. Two, by balancing the weights against the flow up hole, and three, by running Cerberus, which will tell you exactly what you need to do, whether you need to be tractor or whether you can free fall. I hope that answers I think you can check Cerberus online and tell you exactly what it does. I think it's a commercial program. Well, I
Right.
hope that
So
answers the
Russell,
question.
Yeah, in part, it answers that question definitely. And then I have a follow-up question, which is the tool itself, doesn't it kind of limit flow rate? Because then it to some degree, because while it's measuring the flow rate downhole, doesn't it
What we
act like
do,
as a balance?
that's correct. In the program, what you do, you have to enter the tool diameter. So the program is now computed what flow is in the annular space. That's what it does.
I
So it
see.
actually does that. It actually does. It compensates for that. So the dimensions of your tool, the geometry of your tool, is one of the inputs to the program. That's very correct. That's a good question.
Okay, thanks.
Excuse me, I have one question as well. Yes. You hear me?
Yeah, you know, carry on. Yeah.
Okay. So basically I see where all of the measurements are at depths, right? Of course, that's important. So I was assuming that how you got all of that information is that you run it at a depth and leave it there, then you log it and continue. I just wanted to be sure if that's what you actually.
Yes, continue. You can do stationary measure. It does help with interpretation. What does it for the point you raise? We can do stationary measurements, and stationary measurements takes out cable speed and things like that. Those are very, very helpful measurements. We'll take measurements like below the perforations, above the perforation, between. We are not at the moment using it in interpretation, but it helps you to formulate your model and that kinds of things. And it is useful. It's very, very useful information. Yes.
Okay. Okay, thanks.
but Kai, I just want to make sure that you understand. So what Russell just described is, you know how we talked about calibrating the tool, the running speeds, you do it at different speeds. So the stationary locations is also part of that calibration. But when you're actually capturing across the zone of interest, it's typically you would have the tool running, moving up and down.
Yeah, remember what you're doing, right? Remember relative velocity in mathematics. You're measuring the relative velocity between the cable moving down, or the tool moving down, and the fluid moving up. That's why you have to do multiple measurements, right? So one is positive, one is negative. So remember,
Okay.
but when you put the spinner stationary, it removes that element of the cable speed. So it's a very important measurement to make. It helps you with the interpretation.
Okay, I understand. So you can't do one without the other because it would throw
No,
it
no,
off.
no, it helps, but
Yeah.
it helps. Yes, it helps very much. Yeah. And in any interpretation rule, there's never too much information. It always helps you to solve something else. And the thing is, when you're logging a well, be it open or case tool, you don't want to start with interpretation and say, gosh, I wish I had done that. You take all the possible measurements you can, and if you don't use some, you don't use some. But we've never found where we don't use some information. It's always helpful. And sometimes they complement. Sometimes you have a reading you don't understand, and the stationary measurements will help you out. So we
Okay.
always insist on it. Yeah.
Okay. And I also heard it mention open hole logging. A few times
Yeah.
I left the computer. I'm not sure if you mentioned it. What exactly is that?
Open hole logging is like on the first ladder. So when you actually drill a well, there's no casing in that section. Okay. So you're
Okay.
making open hole measurements, and in a nutshell, what you're trying to find out there is where's your oil, where's your water, where's your gas, where's your shale. In other words, that is the beginning of the well. Where's all shale? Well, you got cement in the well. You're looking for exactly where is your reservoir. That's what you're doing. I said we did seismic. Seismic is a time thing. So now you're doing some measurements in depth. So maybe you see a structure on seismic that is so many seconds. You're now drilling that in depth, and you find exactly where your reservoir. Stephen, I don't know if you want to add something more to that there.
Well, that's pretty much it. It's just that open hole logging would be your first pass right after drilling the well, just to confirm that you've penetrated your intended zones. The geologist has an idea from the seismic where they want to go. Then the operations geologist has an idea from his cuttings what formation they're penetrating, and then the open hole log is sort of a confirmation of you're in your right zone and that it contains hydrocarbons.
Okay. Okay, thank you. So what kind of measurements you actually take with the open hole?
They are resistivity, which is sending current measure the voltage and vice versa. They're nuclear using gamma ray sources. They're neutrons using neutron measurement. They're acoustic sonic. They're called MRI, magnetic resonance. And we can go on and on and on. But as I said, to put in a nutshell, you bombard the rock with voltage, current, gamma rays, neutrons, and so on. And the rock now responds in a different way. And the way it responds, the petrophysical character of the rock is what you make a log with. And that's what you actually use now to calculate where you have your oil, your water, your gas. Let me give an analogy, right? As a stupid analogy. You go to the doctor today and he does about 2,000 measurements, right? All kinds of different things. And use all of that now to formulate what's wrong with this guy, right? But
Yeah.
that's a stupid analogy, but you run different kinds of measurements on your body. And he does all these different things and you formulate. That is more or less what you do in an oil well in a different way. But each measurement you do makes a different petrophysical. Remember, one does resistivity, one does porosity, one gives you transit time, and so on and so on. So each one of those contributes to being able to describe the reservoir properly in terms of what Stephen was saying there.
Okay. Okay, thank you for that. Thank you.
Not a problem. I'm here. Good question. Thank you all very much for your questions. If people don't ask questions, I get worried. Yeah?
Understand.
Isaac, you have any questions?
No, sir.
If you all got any questions, my email, I think I will send you another thing, we'll send you you on the recording, you will have our emails, right? You will have a video of it, of course, right?
Yes, yeah.
If you have any questions, you can email Steve or myself, and we can answer the best as you can.
Yeah, this was great. I mean, I really appreciate the time you spent going through the actual examples and stuff.
No, not a problem.
And I know that takes a lot of effort and time. So I really appreciate that.
I mean, I wasn't going to play golf today. Don't worry at all. and my wife probably glad I stayed home today this evening because Steve and I worked all day in the office, and then we left about 2 o'clock. Yeah.
Okay, that's good. That's excellent. Well, Russell and Stephen, thank you so much for doing what you all do, and it is absolutely great. I don't know how else to express how much we appreciate.
I do something. Stephen helps me a lot with the slides and correcting and help me try to put things correctly. So we make a very good team. Very good team. I hope Stephen don't disappear like you remember Tariq, right? Tariq is working, right? How many remember Tariq?
Yes. Yeah, of course. He actually works. I met him. He works with my daughter. So
really?
I
Okay.
I do hear about him every now and then.
Okay. Small world, man.
Yeah. But great. Unless anybody else have any other questions for Russell or Stephen, I want to let them go because they spend a lot of time with us already. So thank you all very, very much, and hopefully we'll do this again next semester.
For sure, not a problem.
Next year.
For sure. I hope I'll see you before then, Ahmed.
Well, yeah, I still have things for you. You just don't.
I have to come and see my mechanic is in Freeport somewhere. Probably coming up next week. Yeah.
All right. Well, I look forward to hearing. I've been hearing this for years, so I can only hope. I live in hope.
I will surprise you next week, right?
All right. Okay. I look forward to that.
Yeah. I go to the Mount Open on. I give you a call and then come up here.
I know. You know how some people who live south, in the north, anything past the Caroni Bridge, they don't. You're the reverse.
Yeah.
We've pushed it to Price Plaza now, Hamid. So
Yeah.
upgrade a little bit.
Wow. You're really pushing the boundaries there.
Oh yeah, push it in the envelope.
All right.
Okay, people, this was a pleasure. You all be safe. Enjoy the holiday tomorrow. I guess it's not a holiday in Jamaica tomorrow. Is it?
Yeah. Thanks so much.
No other
And,
update.
I look forward there. Russell, don't disappoint
Yeah,
me.
no problem. I will. Sure.
Okay.
Okay, you all take care. Have a good one.
Okay, and thanks again. Bye.
Sure. All right.
So, what we'll do, we'll take a short break. So it's according to my clock, it's 6:12. So can we come back around what time? 6:25? Would that work for you all?
Yeah.
Yes,
Fine.
sir.
Sir, I have a question.
Uh-huh.
On some material we covered before. Do I ask it now or after the break?
Well, it depends on whether or not you all want to urgently go to the break or you want to ask the question. I'm open to for you asking it now.
Well, I could ask it now. All right. So I was going through the gas lift example, the graphical method.
The gas of example, yeah.
Yeah, the graphical method. There was a part that I just can't seem to find where how we came by an answer.
So you wanna share your screen? I mean, I don't know.
I suppose I can do that. Let me do that.
I'm making you a co-host.
Are you able to see it?
Yeah,
Yes, sir. All right. So at this point here, I see we did the simultaneous solving and everything. But I don't see how we came by the pressure at depth to be 640.
Yeah, so that's in the so that's the pressure in the casing, right?
Yes, sir. It would
Or
be
not?
the gas pressure indication.
Right. So that's where you have to use the equation that calculates pressure at depth.
That would be this.
Yes, yeah.
About this one here.
So
This
is that okay? So you understand how they go about doing that, right?
I would have to go back through it. I remember we did it in class.
Right. And this is an approximation with those assumptions with a gas gravity of 0.7, assuming a Z of 0.9 and a temperature of 600 degrees Fahrenheit. I mean, degrees Rankine.
Yeah.
That
So
you can use. So this is the same thing. It's an approximation.
okay. So we could use this instead of this equation.
Yeah. I mean, in
Okay.
that different approaches, some more accurate than others. And if you read this one that you're showing here, they tell you that there's a graph that you can get the gradient of the gas in the casing that you can read off based on the specific gravity. But again, it's based on certain specific like temperature. If you go back up, I
Oh,
want to show you what I'm talking about.
okay.
The other, yeah. If you go up,
Yeah.
there was a no, go up again.
Yeah. So this one.
Yes, this one.
Right. I understand that, that's it. I was going through all of these graphs and trying to find
And what they were saying is that so you can use this, but again, this is based on a temperature of 70 degrees at the surface, 190 degrees bottom hole, a TVD of 10,000 feet, all of that. But if you want to be more accurate, the better thing to do is to use like that equation, which we said is on the average temperature and pressure, or you also have the Calinden-Smith type method for and the whole point is static, the assumption that it is static.
Okay. All right.
Yeah.
So yeah.
So you have
But
this.
you have the working out? Why
If
I
what?
asking if you have the working out? Because all right. So what was the starting pressure at surface then?
So in this example, right,
Yes.
remember the assumption is that the in and the out are the same, meaning that in the tubing and in the casing, the pressures are the same. And
Okay.
then what you have to do is to convert that pressure in the casing to the surface. And that is where you manipulate that equation. If you come down, yeah, so go back up. If you were to use this equation, in this equation here, PL is the pressure at depth.
Which would
But
be the
in
depth
our
P.
example, we have that. And what we want to be able to do is to calculate the pressure on the surface. So you make PS the subject of the equation and you can solve for it. Because you get the pressure at depth. And then what you want to be able to do is to work out what pressure you would need on the surface to get that equilibrium curve. If you understand?
No, all right. I understand I understand getting the pressure at the surface, you know. I understand that.
Okay.
And also, I think this equation down here, yeah, I also see you use it in a different document. This is good. I mean, I back calculated and saw that's how we got the 640. No, not the 640, the 560. I got 563, which I mean,
Right.
essentially,
Yeah. So yes. So you got the pressure at depth in the casing, and then you converted that to what pressure you would need on the surface to be able to have that. Yeah.
okay.
Is that clear or not? You don't sound clear.
I, I still having issues seeing where we get the 640. So you're saying we would assume that it would be the same pressure. So at the depth of
No,
5.
no, no. What assume for the first one? Remember the YouTube, right? So you're saying what the pressure is in the casing is equal to the pressure, and that's how you're able to get this equation here. You're equating in the tubing and in the casing.
That is
Okay, so okay,
for what exactly? Because here we're assuming operating conditions. So I'm assuming this is at the operation valve.
right. So you're right. My bad. My bad. Yes, absolutely. Because in this example, this here, it's where you're coming from the surface to the
The
operating valve,
operating
and
valve.
then you're starting from the bottom and you're coming to the operating valve, and you're
Yeah.
solving for that pressure there. I
Yeah,
apologize.
we got the depth. Yeah,
Yes,
we
you are
solve.
absolutely correct. Yes.
I totally understand that part.
Mhm.
It's just and the D equals 5,400. I did the calculation as well and get that. So 640.
So the question is, how did you get the 640? Is
That
that
is
it?
it. Yeah, that is it.
Right. Well, and the 640 should be where you have a pressure on the surface. Well, you will be using the gradient of the pressure of in the yeah.
In the tubing,
And no, it has to be in
in
the
the
casing.
casing. Correct.
Yeah.
Yeah. So
But
that is it. So I was wondering where we get that gradient from.
yeah, so it has to be the well, you can use a graph.
Yeah.
Right. And so you have an injection pressure on the surface.
And what would that injection pressure be? Do I use the
The one
1250?
that you were given.
You mean which were given?
Yeah.
That's 1250.
Yeah.
Okay, so we're using the 1250 then.
Mhm.
So use 1250 and we'll get 0.03 that. All right, so if I use 0.0315,
Well, it's slightly more than 0.03 based on.
I would say 0.0315.
Well, yeah.
0.0315 multiplied by, that's PSI per foot. So multiply by 5,400. I got 170. I get 170 PSI.
170 psi.
Yeah, I multiply 0.0315 by 5400.
Okay, all right. So well, that is
Do
definitely
I,
wrong.
do I add that to anything? All right. So would I add the weather pressure? No.
No, 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 no. It can't
Yeah.
be that.
Right. That's it. That's why I was saying I've been difficulty finding it.
Right. Okay. So let me look at that. Let me look at that. So you all can go on the break and let me look at that. And when by the time you all come back, I should be able to tell you.
Okay, sir.
Okay.
When do we come back now?
Well, it's 6:22. So let's come back at 6:30. Well, 6:35.
Okay, sir. Thanks.
This meeting is being recorded.
Right. Thanks. Isaac. Yeah. So yeah. So now that you found the depth, right? If you plug it into any one of the equations, you will be able to get the pressure at the gas injection point. So if you use this equation, it will be the separator pressure is 100 plus 0.1 because of that rate, and that's how we got that gradient, multiplied by the depth, which is 5400, and you multiply that by 0.1, that comes 540 plus 100. That's how you get the 640. And so what you're doing is you're working on the pressure in the tubing, and so it doesn't account for any drop in pressure in the casing, nor any differential across the valve. And so when we actually doing the design, that's why we include those kind of safety factors to account for that.
Yes, sir. Thank you for
That
that. It was so
that's how you got it.
I didn't see it. I didn't see it.
Right, but that's how you go. That's how you go. It's really the pressure in the tubing that you're calculating.
Yes, sir. Thanks for that.
And you're assuming it's the same thing on the casing. But you and I both know there will be some pressure drop, even across the valve. And so when we're doing the method, the API method itself, that is why you would put some fixed pressure loss across the valves and stuff, right?
Yes, sir.
Yeah. No, but Kai, to be honest with you, I'm really happy to know that you're going through the notes. So that's brilliant.
Okay, sir. Thanks for that.
Yeah, no worries. So
Really
what we're
appreciate
going to
it because I was stuck.
Mhm. Yeah, yeah, yeah. I mean, and that is what you have me for. I mean, so and that's why I have all these little notes, because if you were to go through these things, which you can, you guys could read and understand just like me. Um, you know, that's why I kind of put the notes and stuff so that it's easy to follow. So I will make sure and put that in, because look at, I forgot, and that's what happens. I forget quite a bit, so I need to write things down. But so I need a little time to just kind of refigure it out there, because I never remember. Anyway, but we good, Kai?
Yes, sir. Good.
Right. So what I wanted to do today, rather than continuing with production logging, and there's a lot of information um, on the site that you need to read to be able, well, to understand how the tools work and stuff. And I don't think I need to go through that with you, because I will basically, a lot of the information is there. You need to read it. So are we clear in terms of what the expectation is?
Yes, sir.
Yeah. You know, so that is what is expected, and what I wanted to do for the rest of the day. And if it is that we need to go over some of it, we will, because we have a couple more classes. I wanted to talk about a little bit about formation, and even that you can read a lot of that on your own. Um, so tell me if this is working for you. I'm not trying to shortchange you in any way, but I don't want you to be in front of your screen and I'm reading things off and you're falling asleep. That don't make sense in my mind.
Yes,
But you do need to read it, and if there are any questions that you want to talk about, we can definitely do that. But I mean, the information is pretty clear. Are we good with that or not?
yes, sir. That's workable. We'll ask questions
Yes,
if
I'm good
there's
with
any
that.
problem.
Yeah. Because especially when we're doing it virtual, it's easy for you all to get. I know you get, but yeah. So So the yeah, so we have a whole bunch of stuff on production logging, and I will still try to see if Russell will send me the the um the pack. Although he said, we have it there on the video. Anything that you all, so you understand the value of production logging, right? It is, remember when we talked about as production engineers, you need to be like a detective. You need to be able to discern based on information what's going on with your well, because your primary goal is to maximize, optimize production. And so you need to be looking at, what's the plan, expectation for how your well is going to behave over time. So you need to start off with that. Even from the onset of when you first drill and bring the well in production, if you go back, right, when you were developing the field development plan and getting the authority or the permission to go ahead with your project, you would have um, ran um, some kind of production profile, some kind of economics that justified your project. And so for each well, you would expect it to behave or to produce a certain amount per day, per month, per year. And so you would start off with, this is your plan, this is the expected, how your well is going to produce. And you will be comparing how it's actually producing from the onset to abandonment. That's what you are going to be doing. And when it starts to deviate, then then you would need to be able to discern what's going on with it, even from the onset. Like how you mentioned, you drill a well, you put it on production, you're expecting 2,000 barrels of oil a day, or you're expecting 100 mmcf per day, and it's producing 50. People are going to be looking at you to figure out what's wrong with it. You understand? And so production logging is another um, um, approach you have in your toolbox that you're going to pull out and say, okay, we need to do, after you've done some, obviously it costs money, and so that can't be the first thing that you'd run to. But if eventually you get to that point, you need to do, you have that at your disposal. Um, and obviously you would need to justify it, but that's what you would want to do. Um, any questions on that in terms of the intent? Um, and as Russell talked about, in terms of running it, you can either do it on wireline or what we call E-line, which is electric line, and that's a continuous type readout versus run it on memory or slick line, where you would run the tools in the hole with battery, record data, and only when you come on the surface, then you're gonna be able to download. The risk with that is that the tool failed or whatever, and you didn't get all the information that you could have got. That's one of the big value with doing it real time. You can make adjustments, you see what you're getting, and you can make um, change it up or do something different to improve the quality and of data and so obviously it's more money, so you need to kind of factor that in. And so he talked about things like the flow metering, getting an idea of the quantity via the velocity of flow from each part of your well. And you can, as he showed with examples, you can have all kinds of things going on. And then you can also discern the different phases, so you can quantify the overall flow rate via the linear velocity. You can also then determine what phases you have, what percentage is gas, oil, or water. And so that is the information that you can get. The noise log he talked about, where you listen is a microphone. They typically use it as a leak log. You can also when you go through the notes, you can see in terms of the noise, you can see whether or not you have flow behind pipe, which means that you have flow outside the casing where you may not have a good cement seal, and so you might have some flow taking place there and then coming in through the perforations from a bottom zone, or vice versa from a zone above coming down. So you can also use it like that. He mentioned too, now the technology has gotten where they can actually quantify based on understanding the frequency of sound and stuff, and quantify the actual rate. I know that they use that to in fracking those shale wells. I can't remember what they call it. It's not distributed temperature survey. It's something else, but it's about listening. It basically listening to sound to be able to determine and help them with their fracking and stuff. So somebody can do some investigation and tell us what that is. I can't remember what the acronym is, but it's really listening, it's really sound measurements. What he didn't talk about is that you also have logs to test integrity. So one of the things is like a cement bond log that which basically you can run to determine the quality of cement that you have in terms of the bond strength between, and it's really forming a seal between the cement and your casing and the cement on your formation to form a hydraulic seal. Because one of the things why that is so important is because when you're perforating and stuff, you want the whole benefit of case cemented and perforating is that you have the opportunity to selectively perforate zones of interest as opposed to an open hole where you have everything is connected. That benefit is predicated on having a good cement bond, meaning you have that seal between zones, and so you can selectively perforate. So, for example, you have a water sand below you. Because it's and if you do a cement bond log that gives you information that you do have a good hydraulic seal, you might be tempted to perforate close to the water because you have some level of confidence that you have a good seal, as opposed to if you don't have that information, you might be cautious and stay away from your sand, from your water sand, and only take a fewer um, perforations. Yeah, do you understand what I'm trying to explain? Hello?
No, sir.
You don't understand?
No. I think no, I don't.
Okay. All right. Okay. Well, uh,
Well, if you could just repeat what you were saying.
what I was trying to say is that um, Russell did not mention other
Okay, yeah.
types of production logs. And
Yes.
what I was simply saying is that apart from the ones that he talked about, there's also the cement bond log. And I then went to describe what it is and why it is important. And the example I was sharing was in a situation where you have um, a water sand below your oil or gas bearing zone. If you have confidence that the cement is forms a good hydraulic seal,
Yeah.
you might be tempted to take perforations close to the water sand, because if you don't have a good hydraulic seal, right, then there's a chance when you start to produce your well, depending on whatever drawdown you apply, you can get coning where the water will simply come quickly into your well bore, and your rates are going to fall, and eventually you might lose your well. But
Okay.
if you have confidence based on running a cement bound log that you do have a good hydraulic seal, then you might be tempted to to take more of it closer to the water sand, and therefore have a potentially a higher rate from your well with a certain drawdown. That is what I was explaining. Is that clearer, Kai, or
Yes,
no?
sir, it's clear. So
Yeah.
basically when you run the log, you would have confidence, or you would be sure if it's good or not, or if it needs
Yes,
improvement.
exactly. Yeah.
Okay.
And then there are other things like you can run like a caliper log, an internal, to determine whether or not your tubing, say, or your casing, the integrity of your casing. And what it is, it's a tool that has fingers, and you have these sophisticated ones. And the same thing, you can get a 3D picture of what your borehole, be it your tubing or your casing, and the integrity of it. You can run those things, and all those are considered to be like production logs. So that will be like an integrity type log, if you needed to determine the quality of your tubing or your casing. Yeah. And there may be other type of logs that you could potentially run. But so we have that some of that stuff. What I wanted to talk a little bit, I mean, the last day we talked a little bit about formation damage and things like that, and that's related to production logging, because the whole point about it is that something is not going right, and you need to be able to um, do some investigative work to be able to find out what might be going wrong. So I'm gonna just share with you. This wasn't the plan, but I'm gonna just share with you. I need. How do you share the sound? I
When
don't know.
you select share screen, there's a little, I don't know if I'll see it. Did it turn off? I think it turned off. But if you select share screen again, to the bottom left of the window, you should see an option that says share audio. Did you see it? I don't know if you saw it, Mr. Hassani, but when you share on screen, there's a little option to the bottom left of the window that pops up when you click share screen that you could check. You muted yourself. I don't know if you noticed that. We're not hearing you. Yeah.
Yeah, you hear me now?
Yeah.
Yes. When I do this and I say share system audio, somehow it mutes me. Are you all seeing my?
Oh, I
Yeah,
see.
so it's
Maybe
correct.
maybe just for the video to play, but that's yeah. I don't think that used to happen before. But you could try just playing the video and then turning it back off afterwards.
The cement bond log, or CBL, is an acoustic device used to detect the presence or absence of a cement bond between the casing and formation. The tool includes an acoustic transmitter and usually two receivers located 3 feet and 5 feet, 0.91 and 1.52 meters from the transmitter. The tool, which must be well centered, emits an acoustic signal that is detected by these receivers after traveling one of 4 possible acoustic paths from the transmitter to the receiver. The signal through the casing is likely to be the fastest, since sound travels quickly through steel. As a result, it is the first of the 4 signals to arrive at the far receiver. The next signal to arrive is that which passes through the formation. The cement signal, and finally the fluid signal, arrive later. Cement contacting the casing tends to dissipate or attenuate the signal energy as the signal propagates through the pipe. The greater the area of cement contacting the pipe, the weaker the signal at the receiver. The effect of a good cement job on the received signal, therefore, is to cause the pipe portion of the signal to be weak, while the formation portion is strong. When no cement is present, the free pipe rings rather loudly, like a bell, resulting in a very strong signal. The amplitude curve is universally presented on CBLs and typically displays the amplitude of the first signal to arrive at the near receiver. Since this amplitude is for the pipe portion of the signal, a low amplitude indicates good pipe to cement bonding, while a high amplitude indicates poor bonding. The amplitude signal alone, however, does not reveal the quality of the cement bond to the formation. The variable density log, or VDL, helps in that regard. Also displayed on the CBL, it is made up of numerous closely spaced exposures of the film by the positive wave train amplitudes. The result is a sort of contour map of the history of the wave train over the logged interval. Notice that the pipe portion of the received acoustic signal appears as strong straight lines. The formation signal, on the other hand, appears at different times, since the cement thickness and formation acoustic properties change from one point to the next. In an interval with a very good bond, the pipe portion of the VDL does not show up because the amplitude of the wave train is too low to expose the film. The formation signal, however, comes in strongly. If a partially cemented section of casing produces an amplitude higher than the minimum amplitude measured in a well-cemented zone, a hydraulic seal may or may not exist. The bond index can help in this regard. The bond index is defined as the signal attenuation in the zone of interest divided by the attenuation in a zone with known good cementation. If the bond index is 0.8 or better over an interval of pipe, a reasonable assurance of hydraulic isolation is possible. The interval length of 0.8 bond index required for a variety of pipe sizes is anywhere from 5 to 15 feet, 1.5 to 4.6 meters. The larger the casing size, the longer the interval needed to ensure hydraulic isolation.
The equation for the bond index is expressed in units of decibels per foot, while most amplitude curves are presented in millivolts or percent free pipe. Most service companies have charts to convert from millivolts to decibels per foot, and vice versa.
A reduction in wellbore pressure from the time the cement hardens to the time of the CBL logging run can cause the pipe to shrink from the cement sheath, forming a microannulus around the casing. Even though this microannulus does not permit hydraulic communication, the cement cannot maintain the coupling to the pipe required to attenuate the acoustic signal. As a result, the recorded amplitude will indicate a poor bond. However, during logging, if the internal pipe pressure is increased above the curing pressure, the microannulus will be closed and an interpretable log will result. The travel time curve is the primary quality control curve on a CBL. Travel time is measured from the initiation of the acoustic signal at the transmitter to the arrival of the first signal at the near receiver, which reaches a minimum amplitude level. When the signal is reduced due to a good bond, the travel time signal stretches, since the minimum amplitude level is not reached until a later time. This is known as cycle stretch. If the pipe signal is very low, the first arrival may not reach the minimum amplitude level, but the second or later positive arrival may do so. This is known as cycle skipping. Neither of these effects should be of concern since they relate to a condition of good bonding.
However, shortened travel time can also indicate that the tool is not properly centered, and that the acoustic signal is traveling to the receiver faster through the shorter path on the side closer to the casing wall. Such a situation will result in an inaccurate log. Even if the tool is centered, very low porosity limestone or dolomite formations have faster travel times for an acoustic signal than steel pipe, perhaps by as much as 12 microseconds. In such cases, the formation signal beats the pipe signal to the receiver and a shorter travel time is recorded. Thus, the pipe to cement bond cannot be measured in fast formations.
Right. Did you all hear that?
Yeah, we did.
All right, great. Okay. So yeah, so for the rest of the time, we have about an hour. I wanted to talk a little bit more about formation damage. Right. If I can just, are you all still with me? Are you all,
Yes, I'm here.
okay, great.
Yes, sir. Here.
You all seen my screen?
Yeah, so we could see it.
Right. So what I'm gonna go through this relatively quickly because a lot of this stuff, again, you can read it, right? So, but what I wanted to leave with you is almost the process of you as a production engineer. Um, the process you would need to follow to actually implement some remedial work, right? So we talked about the different types of formation damage and all of that good stuff. And what this talks about is um, the different methods that you have available to you to address some of that damage. So the mechanical methods might include propped hydraulic fracturing, explosive fracturing, and the remain additional perforated. So chemical methods would be the matrix acidizing, tubing acidizing, or the tubing acid wash, or some other kind of organic um, type of treatment. We talked about, hot oiling. We talked about, scale and that kind of stuff. And then the biological method with the microbial simulation, where you actually could pump some bugs with some food, and they're supposed to help by creating some kind of surfactant which will change the interfacial tension and cause the oil to flow easier to the stuff. I did a couple of those um, when I used to work at Trento Beck. There was a company that was trying to sell their bugs. The name of the company was Oppenheimer. And so a couple of expats came down with their bugs. We went to a garden shop. They bought some nitrates or some kind of um, biological food, that kind of food, and get their bugs activated. And then we pumped it into a couple of wells, followed it by some water, and let it soak for a while and then produce it. And I wrote up a little report in terms of production before and after stuff. So that's my, that's the only time I did anything with that. Combine mechanical and chemical methods, and then thermal methods would be like steam. Again, the whole intent would be to decrease the viscosity. I'm sorry, Kent is not here because what Kent talks about is like to get their well to flow, they would pump viscosity reducers, those very heavy crude um, and stuff. So they're not necessarily stimulation, but it helps with the overall rate, increase the rate, and being able to pump their wells. Um, and then you have electrical heating. Professor Hussein was doing something with radio radio waves to generate heat downhole to heat the formation so that your fluids could flow easier. And any questions on any of these to say that you don't understand how what it under reaming. So Isaac, do you know what under reaming is?
No, sir, I've never heard that word before.
Yeah. Paul?
I think that's why you use a reamer to increase the size of the I don't know what they call it, the cavity to the bottom of the hole or something like that.
Yeah. So and if you watch out the objective, they talk about increasing RW. And the reason why you have the equation there is to show you the impact of each of them, maybe, and the overall the rate. So yeah, so if you an under reamer would be where you would drill a hole of a certain size, and then you would run this almost like a bit. So it will actually open out. It will have like arms that will open out, um, and you can then make a bigger hole. And what that does is basically you land up with an RW that is larger than what you had before. And so what that does, if you look at the equation, it will it will cause your rate to increase for the same amount of drawdown. And so please note that when you look at and you compare and they talk about pressure drop and all of that good stuff. It's about how do you go about achieving the rate, and how to achieve that rate. If you have skin, you would need to apply a higher drawdown. So you need to be able to understand that. Anyway, but so yes, and a propped hydraulic fracturing, Kai, you know what that is, right?
I've heard you mention it.
But do you know what the process is?
No, I don't know. I can't explain the process. No.
Okay, no, that's fine, and that's why I'm asking the question, because I want you all to know. Yeah, so the hydraulic fracturing is where you pump fluid at a high enough pressure that is higher than the fracture pressure of the formation. So you actually create fractures within your formation, and you're doing it hydraulically by pumping fluid of a certain viscosity at a high enough pressure that it does that. If you were to stop pumping, the fractures are going to close. So what you do is you pump it, and you pump a propellant, which is like gravel. And so when your fractures try to close when you stop pumping, they are going to remain open because the propellant will keep it open. And this is not like having a diameter of 1 inch or 2 inches, and it's not like that. It's going to be much smaller. But the fact is that you would have created very conductive conduit within your formation that would allow fluid to flow easier into your well. Does that make sense?
Yes, sir.
Right.
Also, one thing you said that the propellant here send down after to keep the fractures open. Those you said it's like grapple. Those one block the flow of the fluid through the holes in
Yeah,
any
I was
way,
just about to ask that question.
or will it block it like in a minimal way?
In a minimal way. So yes. So the point is that the propellant is going to be round. It's not going to be it's going to be spherical. It's going to have a compressive strength that is high enough so that when this overburden comes down on it, it doesn't get crushed. And you will have the intent would be to have a few layers of that's propellant in those fractures. So when it closes, it still has a very high permeability through that layer of propellant, much higher than the original formation. And that is the technique that they use, that and very long horizontals that they've employed in onshore US, where, I mean, I don't know if you know what shale looks like, but shale is like concrete.
Okay.
And they are able to produce those wells economically because of how these very long horizontals and creating these fractures.
Okay, so you're saying
Yeah.
because the horizontals are very long, they have like a greater place for the formation fluids to come into the well bore.
Yeah, absolutely.
Okay.
So if you watch at some of these equations in fluid, they talk about H. So your H is like 2 miles. That's the length of some of these laterals. Yeah. And then to perforate it or to do the hydraulic fracturing, I think we talked about it. We do it in stages. They do it in stages because they can't generate enough hydraulic power or pressure to do the whole lateral at the same time. So they have to break up that long lateral into different. So they would frack a certain portion of it, plug it, frack another portion, frack another, and then open everything up. So, and yeah, so that is the kind of stimulation that we're talking about, and if you look at the others in terms of, we talk a little bit about the acidizing and stuff, but basically it's the same thing. What you're trying to do is to increase your inflow performance, and it could be designed to actually remove formation damage or to improve what you had originally. So we're not talking about you damaged it, but which is what happens in onshore US with the shale. It's not that they have formation damage, it's just that the reservoir itself is just so impermeable that without those employing those techniques, the wells will not flow at a high enough rate to make them economical. Right. So an increased well inflow Q or well stimulation can be achieved by increasing the factor KH or decreasing one of the factors S or RW, RE over RW, or the viscosity, which is what some of these techniques try to address. And yeah, so, and this kind of goes into what we were talking about in terms of the whole intent of what these techniques try to do. And the diagram. So I'm trying to use something here. Um, yeah. Are you all seeing anything on the screen?
Yeah, we could see you right. And
Okay,
Yeah.
great. Yeah, so I wanted to just point this out to you all. The point I was making is, so when you look at this, right, what it shows is that, in the ideal pressure profile, where it is, and then additional pressure profile, where you have damage, and what you can see is that there's a significant amount of additional pressure drop. But all of that is to achieve a Q, a fixed Q. And this is the point I wanted to make, that you need to understand that so in the ideal case, to achieve that Q, you would need to have, the PWF is going to be P2, which is and which is is higher than P3, right? But to achieve that same Q, if you had a damaged well, you would have to have a PWF of P3. And the point is that PR minus P2 is going to be, that is your delta, your drawdown. So this drawdown, because P2 is larger, the drawdown is going to be smaller than PR minus P3. Do you understand the point I'm trying to make?
Yes, sir.
Yeah. And how is that tied back to what we were talking about? Well, just imagine that you have a well where in drilling it or for some reason there is some kind of formation damage. So for you to achieve the rate Q based on your plan, right, you now have to apply a higher drawdown to achieve that rate. And why is that bad? Well, one, you're not going to produce from a cumulative standpoint all the reserves because of that damage, because you're going to have to stop flowing the well because of that. And then the additional drawdown can cause coning or sand movement or all of those bad stuff. You understand? So that's why it is the formation damage is such a bad thing. Please tell me that you all are following or you understand what I'm trying to communicate to you all. No? Okay.
I
Believe me.
I understand. I don't know, but yeah, that's
Yeah. All right. So why is this? I'm not able to move. Okay, there you go. Right. So this is the process I wanted you to appreciate. Um, so you have identified that you have a problem with your well, and what you would need to do is to one do some investigative work to find out exactly what the problem is. But how do you go about justifying um, to go ahead and spend some money and do some stuff. So this is what you would need to do. So an estimate of the duration the well stimulation treatment will increase the well production is also required. These prognoses must also consider the well inflow, whether the well has sufficient inflow capacity and remaining reserves, the well tubing outflow capacity, and whether the production facility have sufficient capacity to process the extra volumes, fluid volume. So you need to consider all of those things. And basically, this here, that increase in production, you would need to be able to quantify that. And that is what you're going to run your economics on to say that you're going to spend X amount of money. And that will lead you to an increase in Q. And it's just not an IP, but it is over some period of time what increased production that you're going to get. And that is how you're going to run your economics. Does that make sense? I'm going to take that as a yes. Yeah. So the job economics and practice. So appropriate discount rate. So Isaac, what is a discount rate?
I would assume that, I guess a company could, the buyer of, let's just say natural gas, would get a discount based on something from the seller.
No.
A specific discount is specific to them. I don't know.
Okay. But so this is about you running the economics, right? And so the appropriate discount rate, since hydrocarbon produced today are more valuable than later hydrocarbon production, which may not necessarily be true in these times. But any reductions in facility capacity while the spent stimulation fluids are being treated must also be included in the economic evaluation. Hydrocarbon production loss while the well was taking off production to carry out the well stimulation treatment. You need to take that. An expected chance that the stimulation will be successful, this is often significantly lower than 100%. So in other words, you need to risk your production profile. What does that mean? So yeah, so this increase that you expect here, you need to risk that so if you say, for example, you were looking like at an uplift of say 50 barrels, declining over some period of time to say 30 barrels. You understand? So that's how you're gonna, and decline curve analysis and stuff will come into it. But basically, based on some methodology, you would come up with this. The appropriate thing to do would to be have like a P90, which means that you would expect with some a high level of certainty to at least get say 30, and maybe on the low end, however you want to have P10 and T90, where it might be a chance that you might get say 70, and you would run your economics based on that range rather than just that fixed expectation. Yes, and so that is what you would want to account for. The deferred production, making sure that your facility can in fact accommodate the extra capacity that you're anticipating, and then risking the actual uplift that you anticipate. So the discount rate is, and it's normally referred to as the internal discount rate. So each company would have its own um, discount rate. And anybody ever heard about NPV, which is the net present value? So the whole point is that the value of money decreases over time, right? And if you want to be able to really compare one project versus another, what you want to do is to really calculate something called the net present value. In other words, value money over time. What's that value today? And so what you do is you discount this money based on that discount rate to bring it back to this net present value. So that's one economic parameter that you would use. Another one could be like your payout, how long it will take for you to pay out how much money you spent based on the returns that you're getting from the investment. That payout or that payback time. So a somewhat simpler calculation method is to calculate the payback time, that is the production time required for the increased net hydrocarbon production to pay back the cost of the well stimulation treatment. The most profitable well stimulation candidate is the stimulation treatment yielding the most rapid payback. Most production companies require a high rate of return from this type of well treatment, leading to a payback time of between 6 to 12 months from this type of well treatment. So I don't know if all of this is going over your head, but so this, are you all still seeing my drawings, and is it blocking that last thing that came up there?
Yeah, so
Yeah,
the
I
end
hear
thing
it.
and blocking the grading.
So let's. Ooh. Paul, I'm just loving this thing, boy. Right. So the discount rate is the rate of return used to discount future cash flows when calculating an investment present value. And a discount rate is applied to future cash flows because money earned in the future is less valuable than the money earned today. And this is based on the principle that money should make more money over time, a concept known as the time value of money. So have you all ever heard anything about, any of this kind of stuff? I know, Paul, you have. Um, Isaac and Kai.
No, not really. I didn't really dabble too much in the economic things for like the past projects I did.
Yeah, but so you recognize though what I'm trying to communicate to you, that as part of what you're going to be doing as a production person is to be able to run your economics, or at least know what's about. So for
Mhm.
your project to be implemented. And this is about, as I said, in line with, you've identified you have a problem with your well, you know what some of the sources might be, you've done that investigative work, you're now planning to do some remedial work. What do you need to do? Yeah, that is what I
Yeah.
want to kind of share with you, and I hope you appreciate that.
Mhm.
So this is the production system again, all that good stuff. One of the things too is that they talk about the reserves. So, if you don't have the reserves, then, spending money to remediate the well and then it's not going to pay back is not a good investment. So that's why they talk about making sure that the well or the reservoir has the reserves to be able to, um, this whole point about, um, having this increase, we call it uplift. So you do the remedial work and you would expect an increase in production. Um, and that profile production or increase uplift is what you're going to run in your economic program. Right. Yeah, so these are some of the questions that you might want to ask yourself in terms of, do you have a good understanding of what the skin is? Does the well show sand production? Is the cause of damage known or at least suspected? And then you go through the process of identification of the cause of the formation damage, greatly increases the chance of matrix treatment success, since you know, a treatment fluid which efficiently removes the specific form. So in other words, what you want to do, like when Russell was talking about a particular example where people were taking the surface data and they were concluding, but they were smart enough to run the production logs, and based on the information they got, they recognized that what they were thinking the problem wasn't in fact the problem. And so that is the point. You need to really try your best to understand the problem so that you can then plan accordingly. And then, having done that, in terms of identifying, coming up with a plan, is the stimulation feasible? The final stage of stimulation candidate selection is to evaluate the practical aspects of the stimulation. What is the mechanical condition of the well? Are there any logistical um, scheduling or other overriding considerations which prevent the well being taken out of production? So, for example, um, so this wasn't to do increased production, but we would have had a well that had casing pressure, which is something that you're not supposed to live with for an extended. We had gotten some deferral from the government, the Ministry of Energy and stuff, but we with a plan that we would fix it by a certain period of time. And the point is why it is that they would have allowed us to do that and understand the risk and manage that risk was because without that well being online, there is a chance, or we could not supply enough gas to domestic or Atlantic. And so that's the point, that you need to be able to um, to understand all of that impact before you do whatever you do. And this is the, again, in terms of the cycle of how, the process is what I'm really want to impart upon you of how you go about doing a simulation job, or investigating it, planning it, and executing it, and learning from it. But the point, though, is prevention is better than cure, and it is much far better to prevent the damage and rather than trying to fix it. Because the point is that, one, in terms of your success rate, but two, you could land up, if you don't really do due diligence, you could land up causing more damage than you started off with. Um, so this is chemical, treatment types, and this is in terms of addressing issues when it comes to drilling, completion, or workover operations, produce or continually injected fluid. So those chemical treatments, those operations would have caused some kind of damage, and then the objectives, and then the location, and some comments there that you can read. So what they're talking about is one, acid, inorganic, and solvent organic washes, matrix acidizing, other matrix treatment. So what is that? Um, so in terms of acid, you would apply that to remove flow restrictions, example, inorganic, wax, scale, kill pills, etc. Um, and the locations of those obstructions or so would be the tubing, the perforations, and the completion. And the completion being like not just only the perforation tunnels, but maybe if you have a gravel pack and that kind of stuff. Um, so you would use acid maybe if you had those kinds of things. So what is a kill pill?
Never heard of it
So
before.
yeah, so a kill pill it would be, I don't know if you ever heard about low circulation, but if you're doing a well or you're doing some work on a well, and basically you're losing fluid that you can't keep up with to the formation, what you would want to do is to heal those losses or reduce those losses. And so what you would do is to pump some type of material that's going to heal those losses. Yeah, those losses. And it could be fibrous material, it could be a viscous type chemical, and it's a pill because it's a small amount that you would spot across wherever the fluids are being lost. And so sometimes when you do that, yes, it heals the losses, because if you don't control it, you're gonna land up where you're gonna have a low circulation where you can't maintain your hole, which provides the barrier to prevent your well from kicking, and so you need to stop those losses and bring it down to some manageable level. But sometimes the material that you use when you want to now produce your well, it can't produce like how you want it because of the material that you pumped. So what you would then have to do is to kind of pump some other stuff to remove that. Um, there was a pill that we used to use when we first started completing the wells in Mahogany, and it was K-Max was the name of it, and it was a viscous type plug pill, because the permeability of the reservoirs were relatively high, and we weren't using the formation isolation valve and stuff. And so to manage the losses, we used to pump this pill, and it had an effect, a negative effect on the backflow, or the flowing of the wells. And so we were fortunate is that because over time it cleaned up for itself because of the high velocity we produce in the wells at. But a way to treat that though was to pump acid, because it was like a polymer based type um, pill. And sometimes I think we use enzymes. And what the enzymes did is when over time, with the temperature increase, the enzyme actually reduced the viscosity and was able to clean up. But anyway, but the point is that in terms of the acid, that part of it, and they call them washes, I want you to pay attention to the fact that it does not go into the formation or the matrix. It basically stays on the tubulars and the outs, that part of the well. And that is why they are called washes. The matrix acidizing is where it goes into the formation, but you're pumping it below the fracture pressure. And so yes, the acid is going into the formation, but you're not fracking the formation. And then the other treatments in terms of matrix treatments will be fracking, where you actually pump it above the fracture pressure, and that's what you do. And so it talks about the location and the depth. You see, that is what that kind of talks about. And so it then goes into, or it provides information about the potential for formation damage caused by matrix stimulation fluids. And you can read that and you know, appreciate that. But the point is that you have rock, you have formation fluids, and you need to test to see the compatibility of that, because even when you do like mud acid treatment, which is trying to dissolve silica and that kind of stuff, that's like a 3-step, and you create fluorides that are like precipitates, and if you don't remove that and get rid of that, it can in fact cause blockage, which is what they're talking about there. The reaction of the formation rock institute with an incorrectly chosen stimulation fluid may generate further formation damage impairment. Such sources of formation include deconsolidation of the rock matrix due to the acid dissolving the cementing material. You have fines moving, those fines move and then plug up the formation. Generation of migrating and smaller diameter particles, and the reaction products created by chemical reaction between the acid and the formation can be insoluble in the spent. So I mean, I'm running it through, but you just need to read it and be aware of it. And some of the other things would be, you know, like, you know, changing the wettability, water blocks. What we talked about the last time about wettability is that oil flows much easier through rock that is water wet. If the wettability of the rock gets converted to being oil wet, then definitely the permeability is going to be to oil is going to decrease. And what water blocks are, we saw with the relative permeability curves, that as the saturation of a phase increases, the permeability increases, and then the permeability of the other phase decreases. And so if you have an increasing water saturation in your near wellbore region, then the permeability to oil or gas is going to decrease. So that's why that is bad. And then prevention is much better than cure. And then in terms of the actual selection of the fluid, it requires doing a lot of testing before you actually implement. And then it talks about, you know, in terms of the basics of acidizing, you know, yes, you're pumping it in the wellbore, you do the washes, or you do the matrix acidizing, or you do the fracture acidizing, and it talks about that. And then it goes into where the formation might be, and and stuff like that. And so you have, I believe, this a PDF file that should be on that talks about the specific formation damage that for the different phases of a well, during the different phases of a well, that you would want to pay attention to. And I believe that is what this document, this PDF is. So Isaac, can you ensure that that is up on the My Learning, please? If you can.
What's the name of the PDF?
I don't know, but it's about one that talks about formation damage and the different phases. It's an old document.
Okay, I'm gonna check now.
Mm-hmm. Right. Yeah. So so you have information there that talks about like fracture oxidizing, matrix oxidizing, and stuff. There's a lot of reading. And the other thing you would need to be aware of is the safety involved, because hydrofluoric acids are very, very dangerous in terms of the impact it has on your skin and stuff. And so, you know, you have certain things that you need to put in place to ensure that the risk is managed. The other thing too, from an equipment standpoint, obviously it is very corrosive, and so the appropriate type of materials need to be, like for your pumps, your tubing, your you know, all of that, your piping. So that's what this kind of talks about. And US dot is the United States Department of Transport. That's what that is, and everybody should be aware of the safety data sheet, what that is about. People need to be properly trained, have the right PPE, you have to use the right material to store it, the right material to pump it, and all of that good stuff. Any questions on that?
Yes, so the PDF is up online about formation damage.
Great. Acidizing, best use is usually damage removal on the connecting from the reservoir to the wellbore. Yeah. So what this talks about is in terms of the difference between fracture acidizing and matrix acidizing, what the difference. But to a large extent, when do you use what? And the what they try to talk about is really there's no fixed guidance per se on which technique you should employ, other than some range in terms of permeability. So what are the criteria, the two big criteria that you would need to pay attention to in determining what acid and what type of job you should do? Would be the lithology and the formation fluids that you have, and then the other thing would be the fracture gradient, the pressure that you are going to be applying to do the job. Right. So the keys to successful treatments are to the identification of a suitable candidate well, which is capable of a greater hydrocarbon production rate over a period of time, and that you have the reserves to be able to do that. The selection of the optimum type of treatment fluid for the removal of formation damage, the design of the operational aspects of the treatment such that the required economic criteria are successfully achieved. So the selection of the best treatment, corrosion control, and so what we haven't talked about as yet would be, because this thing is so corrosive that you would definitely need, when you're pumping it, you need to pump add a corrosion inhibitor as part of the fluid that you're going to be using. Preparation of the well tubing pickling. Anybody knows what that is?
I don't know. I've never heard that term before.
Yeah, yeah. I mean, the expectation isn't that you would know it, Paul. Don't. Yeah. So what happened is that you know, tubing, the piping on the surface, you might have you know, scales. You know, it might have rusting. You might have pipe dope, and you don't want that when you're doing your job to be pumped down and go into your reservoir. So what they will do is they will pump some low concentration of acid and circulate that out of the well. And so that would clean up all the tubing and all of that stuff before you actually pump your job. So that's what that tubing pickling is. It's the surface lines and the tubing that you would do that. Um, and then you would apply the something like a pre-flush, then the actual acid, and then you would follow that up with an overflush. And when you finish with the job, then you would have the backflow. The backflow is really important. What is that? So the expectation is that you would have calculated how much acid that you need to use, the concentration of acid, the volumes of your pre-flush, and all of that good stuff. And the expectation is that it would have contacted all it needs to contact, and the fluid, the acid, would be spent before it comes back up to the surface. If it doesn't, because of for whatever reason, and then you pump that to the processing plant, you could in fact cause a production upset because the acid um, would could cause so emulsions to form. And in the day of BP owning TSP, which are the oil fields, teak, salmon, and pui, they used to do matrix acidizing because it was very fine. The formation is very fine, and the fines used to flow into the near wellbore region, and the production rates from the wells would fall. And so at some frequency, they would actually do some matrix acidizing with mud acid, which is HCl and hydrofluoric acid. And if they didn't have, so part of their job was when they have the flow back, they would treat that fluid before they sent it to terminal, because in the past what they never used to do that. Excuse me. And so they would cause upsets at terminal. So that's why the cleanup and the backflow is really important. So this is, your quick and dirty. You've seen this equation before. How you go about anticipating the effect of damage on production. You basically know this. So again, this is almost like a repeating. So the cleanup, you have the acid washes, you have the matrix where you're pumping it below the fracture gradient, and then the acid fracturing would be where you're actually fracturing it. The other thing to note is that I'm talking about mud acid and HCl and stuff. When you're talking about um, matrix acidizing, it's to a large extent the two categories of type of formations you're talking about is sandstone and carbonates. And so the carbonates, what you would do is you would pump, or you could pump if you're doing an acid matrix acidizing, either fracturing or so is HCl that you would be using. And typically what you would want to do is, so carbonates they have vulgular type porosities, and they have natural fractures. And what you would pump the acid to do is to basically clean them out or to create new ones. Again, those fractures or natural fractures, or the ones that you create, provides a conduit for fluid to flow easier into the wellbore. With sandstones, you the hydrofluoric acid, you typically would be a combination of the hydrochloric acid and mixed with the hydrofluoric acid. Because you have heterogeneous type sandstones, and you would want the HCl to remove some of the carbonates, or that to remove that type of material for the hydrofluoric to be in contact with the actual sandstone and silica and stuff. So yes, so most acid simulation of plastic, which is like sandstones, are carried out with mud acid. This acid is a mixture of the hydrochloric and the hydrofluoric acids. This very aggressive acid is capable of dissolving minerals such as quartz, clays, micas, hence the name mud acid. These minerals are inert to hydrochloric acid alone. And the aggressive nature of mud acid also means that it's a major safety hazard to the well site personnel involved in the treatment. Exposure to acid results in almost instantaneous blistering of the skin, and permanent scarring of the cornea leading to sight loss. So I can't stress upon the how hazardous it is and the measures that need to be put in place. For storage, they have a whole bunch of information about how you should store it in terms of the materials and the bonding, all of that good stuff. And so here it talks about the different types of acids and the concentrations and why it is there's a need to pump HCl with the hydrofluoric acid. And as I mentioned to you before, there are like 3 different phases that it goes through with the creation of the fluorides. And the point is that the fluorides are precipitates and can in fact cause damage if not treated and designed properly. Yeah, so the byproducts can cause, in terms of the problems and limitations, would be the formation of emulsion sludges. Asphaltene precipitation is a real thing. So doing acid jobs on our type of crude, especially land crude, you need to ensure that you understand the amount of asphaltene in the crude. Yeah, so it's in terms of that. And the other thing to note is that the so typically you have with every 10 degrees increase in temperature, the rate of reaction is doubled. So that's something that important. Besides the others in terms of using the right acid, the compatibility concerns and stuff like that, and the acid byproducts. Um, so this is when you use acids and the wrong application kind of thing. So we talked about the pickling, and this just goes into pickling procedure for up to like say 8,000 feet. For deeper, what you can do is, instead of pickling, what you can do is the implementation of the acid job using coil tubing, where you actually spot the chemicals that you bypass the tubulars basically. So there's no need to do the pickling, and so the method would be set a retrievable bridge plug above the perforations, establish circulation with water, and a mutual solvent is something that you would add because it is a chemical additive for stimulation treatments that is soluble in oil and water and acid-based treatment. Yeah. So it prevents emulsion being formed, and also ensures that you leave the rock water wet. So you can use it either as a pre-flush and or an after flush to ensure that you leave your formation water wet. Yeah, so the deeper as I know to just spot it using cold tubing. Right, so I want to stop here. You can read the rest and just get familiar with some of this stuff. I mean, a lot of this is for information only, but you would probably never, well, I don't know if you'll never, but it's good for you to read. But knowing about the different types of formation damage and stuff is important. All right, any questions? I'm sure you have a lot of questions, but it's a lot of information for you to.
So I have one question, but it's not about this PowerPoint. The field trip this Saturday, are we still on fit or not?
Well, you didn't get back to me in terms of remember the question was whether or not who was going to who was willing to buy a safety shoes.
Mm-hmm.
I don't know. I don't know if you got that information from anybody, because I don't know what the numbers are. So if you could get that to me, I'll call Xavier and see if we can do it.
Okay. Okay, I have
Sorry
to
if I
check and see
wasn't
my
clear.
myself.
You wouldn't. Did I not communicate well with you?
Oh no, because Simi just told me that after I told him in the group that we'd have to source safety shoes only. And but I didn't know you want me to ask like the specific
Well,
number
no,
of
I
people.
need what I need. Sorry, Isaac, is that what I need is to find out who is willing to do that and therefore willing to go on the field trip.
Oh, okay. You can find
Yeah,
out specifically.
yeah, no, but yeah. So I'm sorry if that wasn't clear.
Okay.
Yeah. So you think you might be able to get that to me tomorrow?
Yes, I will ask in the group. I'm in the group and ask.
Right. Yeah. So yeah, so that's the story. I don't know. The rest of the stuff you all can read, as I said. Um, it's quite a bit of stuff. But that's there. Okay. What else? Anything else? Kai, you still hanging in there, or you?
Yes, sir, hanging.
Yeah. Because normally I know you run off to work or whatever. But good. Yeah. So anybody went through the ESP tutorial kind of thing to make sure that they understand how it works, how to do it?
I didn't get to that part as yet.
Yeah. Paul, when you gonna start covering my work, man? I know Isaac. What about where are you at?
I haven't gone through the ESP tutorials yet. I was looking through the PDF you had put up on the ESPs.
Mm-hmm.
I was going through that. So that's all I went through so far.
Okay.
But a lot of taken now, so I'll like go through it again and yeah.
Mm-hmm.
The API method.
And I don't know what's happening to the rest of our class. I don't know if they're still doing our class or not. Paul, when you gonna start doing my work, man?
Are you referring to the course material or because I've
Like,
already reviewed I've done a review on the first 2 weeks of classes. I need to
okay, well, good.
catch up. Yeah.
Okay, good. All right. Well, thank you all so much for being here. I mean, I hope you enjoyed Russell's presentation. And I, does anybody have any feedback on the rest of the class? What's their story?
No, sir, I don't.
Okay. Yeah. I know one person dropped out, but I don't know what's happening with the rest of the people. I haven't heard from
Oh.
them for a while. All right. Well, have a good night, and we're coming to the end soon. Paul, when is the last class?
The last class is, let me get exact dates. The 12th of April.
Okay. So we have 2 more classes then.
Yeah.
Yeah. Okay. Well, try your best and go over the work. And if you have any other questions, I'm more than willing to let's discuss it. Yeah.
Yeah. Before we close off,
Mm-hmm.
is there already a deadline set for the Prosper Gap assignment?
I'm not sure, but there should be. I don't know if did I not put an assessment date.
Well, when I look on the portal, I see April 21st.
Well, it can't be that, right? Because exam starts. When does the exam start?
Exam start on the 24th, which means the 21st is probably the Friday before exam start.
Yeah. Well, if you all are okay with that, then we can stick to that. The intent was to give you all enough time. That is the only reason it's pushed back so far. But if it is,
Yes, I'm with
that
that.
it clashes with, you know, your study and you know, it really was to just to give you all enough time.
On the first lecture, Mr. Hasnawi,
Mm-hmm.
1, 2, 3, 4, 5, on the sixth slide, it doesn't have an exact date, but it says middle April is the due date.
Mm-hmm. Mm-hmm.
So I don't know if you took into account that there because teaching would have closed off mid-April. And
Yeah.
yeah.
Yeah, and yeah. So what it is that you are suggesting, Paul, that we should stick to the middle of April?
Well, I don't mind, but if you're asking for the class to decide, I think everyone should come to an agreement on it.
Mm-hmm.
And
Well, boy, well,
but
it
at
only
least
have us here, so we could
yeah,
decide.
yeah,
So
I
let's
was about to
decide.
say that, and given that there's only 3 of us, yeah,
Yeah,
perhaps.
let's decide.
Well, I think we can leave it. Or if you're open, you want to push it further, I don't know. But yeah,
Isaac,
For now, I'm going to the 21st.
Isaac, you need to tip the scale, Isaac.
So I go to the 21st of April.
Tell me, Isaac.
I'm going to the 21st of April, so
Yeah, Paul.
Yeah, so let's go with that.
Okay,
nice.
good with that.
Yeah.
brilliant. Yeah. So but just so that you know, it's going to be individual assessment, right? So what I'll have to do is to set up a schedule where we spend, you know, each person is going to be walking us through their model, and we're going to be asking specific questions to test to ensure or to test whether or not you understand what you're doing and stuff. So that's what the assessment is. It's a one-on-one assessment. So,
Okay. So just one more question about the future, right? What you wanted to know specifically was the student, if the student, how much students will still be interested in going in spite of them having to provide their own safety boots, right?
yes, sir, that's correct.
Okay.
You know, yeah, I need to know the number that actually going, knowing that they have to provide they have to get their own safety shoes.
Okay.
All right. But Isaac, again, I really appreciate you, you know, taking the lead and trying to sort it out and stuff. I really appreciate it. I mean, I hope your colleagues do also.
Yeah.
All right.
Okay, so next
All
one.
right. Yeah. So I mean, a lot of information, and but I'm trying to let you know what is what to focus on. So have a good night, and see you all next week.
Have a good night, everyone.
All right,
Check
so
it.
same thing. Good night, everyone.
Bye.
Bye.